Going on. So, okay. Today was my first day of class. First day of the semester. Pretty good. My schedule's quite good this semester. I'll likely try in class because the classes I'm in will actually teach me something. Which is probably the first time I can say that since high school. At least like for an entire semester. I'm not taking like plant sex or loitering 2 this semester. Inshallah. So yeah. I'm in a processor design in Verilog class, and I've kind of prepared a lot for the class just via working on Punt Engine and reading the books I read last year, namely, at first, Getting Started with FPGAs, and later, Advanced Digital Design with the Verilog HDL. And so, I kind of have a funny idea just to one-tap the textbook for this class in one day. I think it's possible, 200 pages. Just got on my last class, which was processor design. It's 3:30. Probably get a better around 11:30. So hit a 8-hour session on this. Should be pretty doable. Likely won't be doing too many exercises, but I don't really think that's the style of this book. We're just looking at the chapters. Basic knowledge to understand FPGAs. What is FPGA? FPGA structure. Up to page 87, I think I would just be reading consecutively with no going back up. Design flow and design tools. That could be kind of arbitrary, but I've used both Xilinx and Quartus, though I'm not a master of either, so perhaps that'll be useful. Design methodology. I'm not too sure what that means. I guess the designing the inputs and outputs of circuits, perhaps. But that's the point of reading this. Perhaps the most important one for me, because I feel like I have a pretty bad intuition for hardware out. Wait, did I? Yeah, because I know I have a bad intuition for hardware algorithms. Will be this chapter, hardware algorithms. Practical applications and advanced devices. Kind of feel like suffixes to this, so I'm sure I can read those fine enough. But yeah, I'm really looking to this for the semester in general. I went to online compilers lecture today. I wish it was more geeky. Like, I don't know. That is kind of the thing with a bachelor's degree. You just you learn nothing about a lot of things. Or not nothing, but you're just not immediately useful in anything. So even as someone who spent like most of the last year working on compilers in some form, taking compilers doesn't really make me truly great at anything about them. So we'll see. I thought it would be a nice exercise to do. I've heard people in the past writing their compilers in Haskell and other stuff because I just read that was kind of the whole point of me reading the Haskell book. But it'll likely be in C++. And it's also a group project, which kind of changes the dynamic a bit. But yeah, I'm gonna get a tea brewing and then have a nice fat stream with this. So I'm also in second course linear algebra 2 effectively. And I thought it was gonna be, imagine linear algebra 1 in the textbook is chapter 1 to 6. This would be 6 to 12 or something, but it's more just going over 1 to 6 more in depth, which is kind of useful because it allows me to not need to review what an eigenvector is and all the algorithms for deriving eigenvectors and all this other junk that I don't even know by name at this point. So that'll be kind of convenient. I can skip over reading that more introductory book, and I also simplified the book list a bit because instead of reading this book that I kind of critiqued for looking like Scheisse before. It's gonna be Introduction to Winry Algebra by Gilbert Strong, something like that. Yeah, I'll be back in a second. Some matcha tea bags. You see how many tea bags in it. So yeah, I kind of wasted some time. I was making my tea and doing dishes and etc. Alright, yeah, talking about algebra, this is gonna be free. First chapter free. Just not yet every cycle. Let me just hit an email check. That'll be looking at IP. So just burn these checks out of my phone. Just not you did every cycle. Let me hit a quick. Nerds yapping. Alright. Respect. So yeah, let's just shut up and do this. An FPGA is a wonderful digital device which can implement most of the practically required digital circuits with much easier effort than other solutions. For understanding FPGAs, logic algebra, combinational design, sequential design, timing analysis. Briefly introducing all of those. The position of FPGA among various digital devices to discuss. 40-year history, SRAM style FPGAs, and how Xilinx and Altera/Intel have become the major vendors. Various small vendors and their attractive trials that are not existing now are also introduced. Interesting. So logic circuits, field programmable gate arrays, a logic device that can implement user-defined desired as well logics by programming logic functions. To understand the structure and design of FPGAs, so we have some external. What is this linked to exactly? These linked to, yeah, that's fine. We're not gonna ping the link tree here. Let me make sure the audio is on as well. Yeah, we're good. All right. In logic algebra, also called Boolean algebra, all variables can either take the value 0 or 1. Logic algebra is an algebraic system defined by the operators and or and not applied to such logic values. 0, 1, indeed. And or not are binary or unary. In the case of not, you have the dot for and, plus for or, and bar for not. Pretty standard. And you have some theorems in this algebra. You have the 0 element that x dot 0. So this is like that makes it associative, yeah. No. Algebra laws defs. What do they call it? Commutative. What's the one? Or it has an identity. That's the identity. Should have paid more attention to my high school book. Neutral element. Or no, sorry, this is identity. This, I don't know what you call this. I'm gonna just shut up and stop acting like I know what I'm talking about. So, indefinite law. Yeah, this is like x dot x is equal to x. Oh yeah, I keep forgetting this is not dot. I just came out of linear algebra lecture. I was thinking this is dot product and addition. I'm cooked. But it's actually the complete opposite of that. X dot 0 is and. Yes, x and 0 is 0, x or 1 is 1 indeed. X and 1 is x, x over 0 is x. Yeah. X and x is x, x or x is x. You got not x is not as x. X and not x is 0, x or not x is 1. X and y equals y and x. So that's the commutativity, associativity, distribution law. So you can distribute the ands within the ors to get a sum of products, and vice versa with a product of sums. Absorption. X or x and y is equal to x. Because if this is true, this is true. If this is false. Yes, certainly. X and x or y. This is true, this is true, if this is false. Or when it's and, this has to be true anyway, because, yeah, okay, so this part doesn't matter. And De Morgan's not x or y and not is equal to not x and not y, and vice versa. So that's understood. Equals is equivalent. Logic equation. A logic equation consists of an arbitrary number of logic operations. When a logic equation is formed with n logic variables, it is a result of its result is either 0 to 1 according to the procedure represented within the occasion by substituting 0 1 into the variables 2 to the total. Yes. Following an arbitrary combination that is a logic equation represents a logic function f of x1 to n. Priority is not defined by parentheses and is given higher parentheses. So yeah. And operator is often omitted. Arbitrary logic functions can be represented by logic equations. There are a lot of logic equations representing logic function. Thus, by giving some restrictions, logic function can be 1 to 1 corresponding to a logical equation. It is called the standard logic form. Single variable or its inverse is called a literal. Logical and of literals which does not allow duplication of itself is called a product term. Sum of products forms a logical equation with only logical OR products. Indeed, a product term formed from all literals is called a minterm. A sum of products, a product term formed from all literals is called a minterm. Okay. A sum of products only containing midterms is called a sum of products canonical form. A product of sums is a dual of a sum of products. A max term is formed with OR of literals. For all inputs without duplication, a product of sums canonical form is formed with max terms. At first, I was not liking this, just saying sentences with no structure, but I kind of mess with this. A lot of other books should have a paragraph for each of these. Just read it and understand what it is and be fine. And if I need to come, perhaps I won't remember that a product of sums is a dual of a sum of products. Like I haven't heard that, but if that comes up, I'm sure I can recall it. Truth tables. So we know what truth tables are. Truth tables represent all combinations of inputs, complete representation of the circuit. Specification of common circuit is defined in the form of the truth table for n inputs. The number of entries of the truth table is to the end. Yeah. Unique representation of a logic function. Straightforward implementation of truth tables is called a lookup table, which is used in major FPGAs. Indeed. From a truth table, two canonical forms such as sum of product and product of sums can be induced. Derive by making the minterms of the input variables when the corresponding output is 1 and then applying the OR operator. On the other hand, product of sums canonical form is derived by making the max terms of input variables when the corresponding output is 0 and then adding the AND operator. So I could use a clarification on that. Combinational circuits. Logical circuit can be classified into combinational or sequential, whether it includes memory elements or not. Indeed. So this is a very long sum of products. It's actually an exhaustive sum of products. And so here's your 2 to the n, 8 by 3, and your outputs, excuse me, as defined by f. Excuse me, sorry. Let me see if my tea is cold enough to move into my pot. Just leave it at that. All right. So I believe I was at sequential circuits. Excuse me. Including memory elements is called sequential. Ah, scheiße. Kruta. Attack. Okay. So yes, they have memory elements. You have synchronous and asynchronous ones. In synchronous ones, outputs and internal states are changed synchronously with a clock signal. Asynchronous ones are level triggered. What does that mean again? Edge versus level triggered. I'm goaded. I'm gonna ask GPT if that's the same. Gen X, escape X, tab, new, O1 mini. This O1 mini task is synchronous versus async circuits the same as edge versus level triggered? Question mark. Third window, stream, back to first window, escape, enter, mouse enter. They are not the same. Okay, yeah, so edge triggered changed their state on clock signal transitions used in synchronous designs. Level trigger devices change their state based on the level of the clock signal, but not necessarily as transition, and can hence be used in synchronous and asynchronous designs. Okay. Taijit. Only synchronous circuits used in most FPGA design are introduced. And or not NAND nor XOR. XOR. No X or yes explicitity here. Outputs of synchronous circuits are determined by both the inputs and the memorized values, indeed. They are represented with finite state automaton. Mealy and more. Shout out. Finite state transducers as partially applied for as partially applied pure functions. Shout out writing, Loki. Big writing head. But yeah. Следующий. Outputs are determined by the internal states of inputs in the memory machine, while in the Moore machine they're determined by the internal states. Well, in the Moore machine, internal states, yeah. Moore machine can decrease the size of the circuits. Or is it the other way around? Moore machine can decrease the size of a circuit since a smaller number of states are required for the target function. However, outputs are directly influenced by the change of input signals. I think this is wrong. Milling machines require fewer states. I'm going to Piazza. I know this isn't really necessary. Oh, let's go. Oh, let's drop the canvas page. Давайте. Bro is woken up. Procession sign. Is it a piazza or a discussion type? В наш новый дом все без будет. Я знаю, где-то высоко. Я и знаю, где-то высоко. Student join classes. Piazza. Shit. Piazza shit. How do you respond to something? Я знаю, где-то высоко. Oh my god, I'm horrible at singing. Alright. I'm also gonna look at my OS canvas because it now exists. So one sec. Would exist in perhaps the most primitive way possible. And we're using GitHub Enterprise. I don't hate myself. So I'll also probably do a speed run of the, what do you call this? Spec of the XV6 operating system. We're moving embarrassingly slowly here. It's already been an hour. Looked. Alright. So here we have a melee type FSM. We have an input X. It states Q and Q prime and output Z. So the input X is directly used to compute a combinational output function to produce output Z. Whereas in the more type, the output function is defined in terms of Q only, is not a function of X. Synchronous logic design. All states of the system are idealized to change synchronously. Let me also, sorry for the spam here, but let's go back to this. Let me do processor design, Piazza. Dude, can't wait till people learn what hyperlinks are. Oh, they use iVerilog instead of Verilator. Curio. Pin this, type dire-moi. Guys, yeah, let me check on my T again. Yeah, one sec. I'll just switch to this. It's too good in the habit of not leaving. Got flip-flop, 1-bit memory element called a flip-flop. D flip-flops embedded in basic blocks of an FPGA change their outputs at the rising or falling edge as configured of the clock. Their edge trigger type. The symbol and truth table of a D flip-flop shown in 1.4. Here it stores the value at D input at the rising edge of the clock and outputs it at Q output. Setup and hold time. CMOS D flip-flop has a master-slave structure consisting of two latch circuits, latch loop circuits, each of which uses a couple of transfer gates and inverters, not gates, as shown in figure 1.5. So we're going to look at these figures in a second. A transfer gate takes the role of a switch and it changes to on-off according to clock. The front-end latch stores the input with the inverse of the clock in order to avoid the hazard of appearing just after the change of the clock. The front-end latch stores the input with the inverse of the clock in order to avoid the hazard appearing. The hazard appearing. What hazard is implied? The hazard appearing just after the change of the clock. So I'll try to define that when we look at the figure. When clock equals 0, master operating. When clock equals 0, master operating. No idea what master operating is. D input is stored on the front end latch, while the back end latch holds the data of the previous cycle. Since the transfer gate connecting the front end to the back end is cut off, the signal is not propagated. Okay, so we got kind of cut up by some figures here. Let's review. So this looks like a higher level schematic for a D flip-flop. This looks like low rising edge, high falling edge. Dx Q is equal to Qn, not Qn. So what is Qn? Yeah, so I couldn't tell you what Qn is. Or we're distracted. So stop complaining about my bitrate, dude. I have 0 viewers. X don't care. So when the clock is low, and Q. So this is not Q. Oh, okay. Q and not Q. What's the point of not Q? What? Why? What is the point of not Q? Типа щица. So clock D going down into this. Oh, not Q is used. How much calf is in this? 200? Damn. Thanks for doxing me. Doxing me. It's just the compliment. It just exists. Llama. So we have a master slave D flip flop. So it's from high to low. High to low, and it's set up by waiting it. Something has to be high, and then it has to be low because you knot the clock. And then the output is German. Okay. It's master transfers the input, clock equals 0. So the slave is refreshing. Master open, slave clock closed, slave D open. Output asserted. No, master transfers the input to here. Then slave, this is lifted. This is asserted. I'm gonna just not care, Loki. I don't think that's as relevant. Input D. Propagation delay of D. The clock rises in that middling state. Then you're metastable for some time. The whole time. Output delay. So what defines this? Dang it, I meant to say netlist in class today when I said register transfer level. What a blunder. Poisson route. Must verify logic and timing. Verified by register transferable simulations. Since dynamic timing analysis by post-placing route simulations with data requires a large amount of computation time, static timing analysis is used instead. Yeah, I've read about that. It can be executed only within a netlist, and comprehensive verification can be done. Moreover, since it basically traces the circuit only once, the execution speed of the STA is high. It is commonly used in other EDA or EDA tools, electronic design automation tools, besides FPGAs, does certain cope with the increasing size of target circuits. Timing analysis includes the setup and hold time analysis for timing verification. It verifies whether the delay of the design implemented on the FPGA satisfies the timing restrictions. Wiring delay depends on the mapping and routing of the design to this resource of the FPGA's composition result in the place route tool. Design is relatively easy if the performance and number of gates of the target FPGA are large enough, but the size of design uses almost all of its resources. Place and route can require a considerable amount of time. The delay of the elements and interconnections while passed must be checked, including the timing margin, so as to certify whether the setup and hold time is satisfied. Single clock synchronous circuits. Since FPGAs have a large flexibility in place and route, synchronous circuits are widely used. Thus, the target of static timing analysis is focused on synchronous circuits. Well, yeah. Although static timing analysis is fast, the target circuits can have a certain limitation. Dude, I always spill junk on myself. Like a 2-year-old. It's so cringe. That's actually so cringe. Since FPGAs have a large flexibility in place. Yeah, I already read that. What do you mean, bro? No, I didn't actually. Did I read this? Since FPGAs have a large flexibility in place and routes, they're widely used. Focus on synchronous circuits. Although the SJ is fast, target circuits can have a certain limitation. Start point, the endpoint of the delay analysis must be a flip-flop with the same clock input, and the delay between them is accumulated. Indeed, the transient time of the signal is different since the wiring delay is not the same. Thus, an FPGA design receives all input data at flip-flops and output data through flip-flops, as shown in 1.8. In other words, the system circuit work with the same edge of the same clock. Is that true? What if you're crossing clock domains? Or is this saying that static timing analysis is local to a clock domain? Let's consider that. So, let's GPD this. Here should just be a simplification. Precondition of the synchronous design is to deliver the clock to all flip-flops at the same timing. Unless you have some pretty bad, or I mean, unless you have clock skew, I guess, which is certain at some capacity. The wiring length of real clock signals is often long, and so the wiring delay becomes large. Also, the fan-out influences the delay time. Because of their influence, clock timing is slightly different for each FF. This effect is called clock. Okay. Goated. Jitter is a fluctuation of the clock edge by the variance of the oscillator or distortion of the wave. Or to deliver the clock at the same time, such skew or jitter must be managed under a certain. So it must be accounted for largely in the worst case for static timing analysis. The clock skew influences the cycle time as well as the delay of logic gates. That is, the most important step in integrated circuits is the clock tree design. In the case of FPGAs, the hierarchical clock, it's already embedded with global buffers providing a high drive capability in the chip to distribute clock to all flip-flops. And thus, a low skew clock distribution can easily be achieved. Compared with ASIC designs and FPGAs, the design step for clock distribution is easier. Position and history of FPGAs. So I'm not too concerned for this. We're going to skim. What is our IC? Integrated circuit, yeah. Don't care about that. Don't care about the 1980s. Don't care about the 1990s. Look, you don't even care about the 2000s nor the 2010s. Chapter 2, what is an FPGA? An FPGA is a programmable logic device, which is a type of integrated circuit that can be used in any digital circuit. So the key technique is how to make programmable hardware devices. After the brief discussion of the structure of traditional IO-style FPGAs, the technology for programmable devices, anti-fuse, EEPROM, and SRAM is explained in detail. I actually want to know this. So I haven't read this. This is a bit deeper than I've gone before. Then logic circuits representation with product term lookup table and mux type basic logic element are introduced. What is an FPGA? An FPGA is a programmable logic device which is a type of integrated circuit that can be used to implement any digital circuit. Indeed. The name of FPGA is the fact the user can use a gate array that is programmable on the field of any workplace. However, the structure of FPGA is not such as indeed you have lookup tables and registers and wires and maybe other things if you have niche FPGAs. Figure 2.0.2.1 shows the structure of a typical island-style FPGA. The basic part of FPGA is divided into three parts. The first consists of logic elements, LB, that realize logic circuits. The second is the input-output elements, IOB, which is input and output signals to and from the outside. The third is wiring elements, such as switch block, SB, and the connection block, CB, connecting LBs, logic blocks, to IOBs, IO blocks. Other than that, there are a clock network, a configuration scan chain, and a test circuit. Conventional FPGAs also contain circuits. You have switch blocks and logic blocks and connection blocks and routing channels. Multipliers, some processors, block RAMs, block memories. Logic element, there are three major program logic implementation schemes. Lookup table, muxes, generic array logic. Either method consists of a programmable part that can be used to realize any logic circuit, a circuit that holds logic values such as flip-flop and selectors. Input-output element is a block that contains I/O pins and internal wiring elements. It also has some control circuits such as put on, put up, pull up, pull down, input-output directions, slew rate, up and drain. In addition, it contains a circuit for holding values such as flip-flops. Commercial FPGAs at several standards are supported, such as these. There's a single-ended standard LIOs. And LVDS of differential standard I/O wiring element consists of wiring channels, connection blocks, and switch blocks. Of the connection between logical blocks and between logical blocks and I/O blocks. Between the island style and original lattice pattern, there are wiring changes of hierarchical structures and those constituting H trees. Each switch is programmable and it's possible to form any wiring route by using the wiring resources. Other elements, logical functions and connection relations of all logic blocks, I/O blocks, switch blocks, and connection blocks are determined by the configuration memory values. The configuration train is a path that sequentially write the configuration data bits to a first remaining module. Basically, the configuration data are serially transformed, but set and read back are possible. Besides the configuration chain, there are other device scale networks such as the scan path and the call network. Others include circuits to support LSI testing, embedded circuits for dedicated functions such as embedded processes, block memories, and modifiers. In Boolean logic, a product term is a conjunction of literals, indeed. Programming technology, as mentioned above, the circuit in the FPGA is controlled by a programmable switch. The programmable switch can be made using various semiconductor technologies. So far, EEPROM, flash memory, antifuse, and static memory, SRAM, have been considered. Among these technologies, the flash memory, antifuse, and static memory are the three types of programming technologies used in the most modern ones. In this section, there are compared and summarized regarding the advantages and disadvantages. Flash memory. The principle of flash memory. Flash memory is a kind of electrically erasable programmable read-only memory. Electrically erasable programmable read-only memory. Read-only memory that you can also erase and edit, which classifies as non-volatile memory. Really? I thought it would be volatile. I thought volatile means it is erased when power is removed. It does.
Loading gate, control gate, polysilicon, source drain. Control gate. I don't care about that.
All right, so despite just drinking 200 milligrams of caffeine, I accidentally just fell asleep. It happens. That's high security if you're trying to not let other people edit your memory. But it's non-volatile. Reverse engineering is also impossible, almost impossible, but it cannot be reprogrammed. Static memory technology. CMOS type static memory. Saw the diagram on the left is a gate circuit. Dude, how did I just fall asleep randomly? I just took a little nappy. You know how it is. Happens to the best of us. One sec. So I kind of blundered by just falling asleep spontaneously. I also have food in the air fryer. So let's just continue. Static memory technology. Information is stored in the bit bistable state 0 and 1 of the flip-flop. So it has words, it appears. Voltage drain minus threshold voltage. I think that's a bit outside my scope. This is more about... I don't need to go too far into the memory representation, I don't believe. Static memory for programmable switches have a lookup table in the logic block and use a multiplexer or something similar to switch the connection of the wirings. The lookup table is the memory itself storing the truth table of the logic expression that's composed of static memory of several bits. On the other hand, a static memory is also used for switching a selector to determine the connection of the multiplexer. It's called an SRAM type FPGA. Pros and cons. Reconfigurable. It's volatile, but I mean, that's also a pro, and then that's reconfigurable. Antifuse. So let me just go to the table. Flash memory is non-volatile and reconfigurable. Medium area. Flash process. High resistance. Has a lifetime. Antifuse is non-volatile. Small area. No in-system programmability. Low switch resistance. 1 lifetime. Static memory is not... It is volatile. Easily programmable. Large memory area. Infinite lifetime. Logic circuit representation of FPGA. Hereafter we discuss how a design is implemented on FPGAs in the majority vote circuit. Oh, okay, this actually is there's a circuit that takes a majority vote. Oh, never mind. I thought it was like some voting algorithm to determine the placement of things. It is a circuit that takes the majority vote of 3 inputs, and the LED glows when the result is 2. In order to realize this, push button, chrono map. Because the logic block of the FPGA adopts the lookup table method, an arbitrary logical function up to a number of inputs can be implemented. Product some standard form. Buffer is inserted in the output stage to improve the drive capability. Decomposed circuit is connected inside the FPGA. Here's an example of the product term where it is principal. PLA, couple logic array. Truth table. It's just the majority of 3 elements. And that's AB or AC or BC. That's kind of smart. AB or AC or BC. Yeah, that's kind of smart. It wasn't immediately obvious to me. IO pad, routing wire in the FPGA, logic blocks, the major road circuit, routing wire in FPGA, output buffer, and IO pad. Looks good. So this is if it was just the circuit, but it's actually configured in logic box, connection box, switch box, and IO box. You have an AND array and an OR array. Okay. The rhombus at the intersection. Programmable switch. Black color indicates that it's on. In the AND array of this example, A and B are inputted to the first AND gate, A and C are inputted to the second AND gate, B and C are inputted to the third. By lookup table, yeah. Two to the K cells, 2K input multiplexer. So I'm gonna get to structure and then check on my air fryer. So you have an SRAM cell multiplexer. It's like merged multiplexers, XYZ. 2 to the third, 3 input logic functions. So you're kind of constructing a table out of nested multiplexers. All right, one sec. I find something to watch while I eat. Classic problem. Tonight we got 2 Costco Chick-fil-A's with chili sauce. And a Blue Moon. I want to read CPP Smart Pointers.
Come up a lot
Alright, so-
recently in my videos, and people requesting this and what is a smart pointer, should I be using smart pointers and all that. Today we're just going to talk about what they are. We're not really going to get into depth about why I
Make sure I don't
think you
dip my
should or
nose in my
shouldn't
food
be
right
using them and all of that stuff, and my opinions about smart pointers in general. I'm going to save that for another video. Today we're just going to focus on what a smart pointer is and what it can do for you. So earlier we talked about what new and delete does. New allocates memory on the heap, and delete is needed to delete that memory, to free that memory, because it won't be freed automatically. Smart pointers are a way to automate that process. That's all that they are, right? Smart pointers mean that when you call new, you don't have to call delete. And in fact, in many cases with smart pointers, we don't even have to call new. So a lot of people tend to have this kind of programming style in C++ where they never ever call new or delete. And smart pointers are basically a way to make that happen. So smart pointers are essentially a wrapper around a real raw pointer. When you create a smart pointer and you make it, it will call new and allocate your memory for you. And then based on which smart pointer you use, that memory will at some point be automatically freed. So let's take a look at the first kind of and simplest smart pointer that we have, unique pointer. So a unique pointer is a scoped pointer, meaning that when that pointer goes out of scope, it will get destroyed and it will call delete. We actually talked about how object lifetimes work and how you can leverage the power of stack allocation and all that in the last video, so definitely check that out if you haven't already. But that is basically how scoped pointers work, or unique pointers. The reason they're called unique pointers is because they have to be unique. You can't copy a unique pointer, because if you copy a unique pointer, the memory that it's pointing to, you'll have 2 pointers, 2 unique pointers pointing to the same block of memory, and when one of them dies, it will free that memory. Meaning that suddenly that second unique pointer you had pointing to the same block of memory is pointing to memory that's been freed. So you cannot copy unique pointers. Unique pointers are for when you want a scoped pointer, and that is the only reference to that pointer you actually want. Let's take a look at an example of a unique pointer. So the first thing you'll need to do to get access to all of these smart pointers is include memory. Now we have this entity class here. All it is a constructor and a destructor. We print when we create the entity and when we destroy the entity, just so that we can kind of look into the behavior of these smart pointers. So over here in main, if I want to create a unique pointer which lasts in a certain scope, so I've made a new scope here, an empty scope, and inside here I'm going to allocate my entity using a unique pointer. The way I'll do that is I'll type in std unique pointer. I'll give it the template argument of entity, and then I'll give it a name such as entity. And then I've kind of got 2 options. I could either call the constructor here and type in new entity like this. Note that you actually won't be able to do this kind of construction, because if you look at unique pointer, the constructor is actually explicit, meaning that you do have to call the constructor explicitly. There's no implicit kind of conversion or converting constructor. So that's one way to make unique pointer, and then you can kind of access it like you would anything else. If I wanted to call a function here, we don't even have any functions, but if I were to call a function here, I would just access it through the arrow operator, and everything would be exactly the same as if this was just a raw pointer. The preferred way though to construct this would actually be to assign it to std make unique with that entity there. The primary reason that that's important for unique pointers is actually due to exception safety. We'll talk about exceptions at some point in this series. I don't like exceptions at all, so that's going to be an interesting episode whenever that happens. But anyway, the preferred way to make this is to call make unique, because it is slightly safer. If the constructor happens to throw an exception, you won't end up having a dangling pointer with no reference and thus a memory leak. Anyway, the idea is that once we make this unique pointer, we can call whatever method we want, and you'll see that if I hit F5 to run my program, our entity gets created here, and then if I hit F10 to get out of the scope, our entity is destroyed now. Okay, so automatically when this scope ends, our entity gets destroyed. That's the simplest smart pointer that we have. It's very useful. It's got a very low overhead. It doesn't really even have an overhead. It's just a stack allocated object, and when that stack allocated object dies, it will call delete on your pointer and free that memory. The problem with this is, as I mentioned, if you want to copy that pointer, if you want to kind of share that pointer, maybe pass it into a function or have another class store it, you're going to run into a problem because you can't copy it. And if you take a look at this, if I was to try and make another unique pointer here called E0 or something like that and assign it to entity, I actually can't do that. And you'll get kind of an error message here, which looks a bit weird. If you go to this unique pointer definition and you actually scroll down a bit, you'll see that the copy constructor and the copy assignment operator are actually deleted, which is why you get a compile error if you try and do something like this. And that's there specifically to prevent you from digging yourself into a grave, because you cannot copy this. Because again, as soon as one of these unique pointers dies, they all essentially kind of die because the memory, the underlying memory of that heap allocated object gets freed. So if you like sharing, that's where shared pointer comes in. And shared pointer kind of works a bit differently. It's a bit more hardcore, if you will, because it does a lot of other stuff under the hood. The way that a shared pointer is implemented is actually kind of up to the compiler and the standard library that you're using with your compiler. However, in pretty much all systems that I've seen, it's using something called reference counting. We're going to have a specific video about reference counting. And in fact, a lot of these things in the standard library, we're actually going to have videos where we implement them ourselves, because they're great examples of how C++ works and how we can kind of use C++. So we're going to definitely write our own unique pointer, smart pointer, shared pointer, all of that kind of stuff in the future, as well as other kind of standard library features. So if you want that, that's coming. But the way that shared pointer works is via reference counting. And reference counting is basically a practice where you keep track of how many references you have to your pointer. And as soon as that reference count reaches 0, that's when it gets deleted. So as an example, I create one shared pointer, I then create another shared pointer and copy that. My ref count is now 2, so 1 for the first one, 1 for the second one, that's 2. When the first one dies, my reference count goes down 1, so I'm on 1 now. And then when the last one dies, my reference count goes back to 0, and I'm dead. So the memory gets freed. So to use a shared pointer, you just type in std shared pointer. Let me just get rid of this compile error. We'll do entity over here as the template parameter. I'll do shared entity as the name, and then I'll set this equal to std make shared entity. Now, in this case, you could have also done a new entity like this, and you can see that compiles fine, except you definitely don't want to do that with shared pointer. With unique pointer, really the only reason not to call new directly is because of exception safety, but with shared pointer, there's actually going to be a difference, because shared pointer has to allocate another block of memory called a control block, where it stores that reference count. And if you first create a new entity and then pass it into the shared pointer constructor, it has to allocate, that's 2 allocations, right? Because you're constructing the entity first, and then the shared pointer has to construct its control block. Whereas if you do make shared, it can actually construct them together, which is a lot more efficient. And also, for those of you people who hate new and delete, this obviously gets rid of the new keyword from your code base, because you're just calling std make shared instead of new entity. So I bet you guys love that. So with shared pointer, you can of course copy it, and yeah, I mean, if I type in code like this, it's going to work perfectly fine. I could also move this outside to here and just have this over here. Let's make another scope for fun so I can kind of demonstrate how this works. I'm going to drag this over here. All right, so I've got kind of 2 scopes here. In the first one, I've got E0, that's it. And then in this one, I have my shared entity. I'm going to assign E0 with my shared entity. I'm just going to comment out or get rid of all that other code with the unique pointer. So now what will happen is, if I hit F5, the first thing that's going to happen is I'm going to construct my entity. So that's done, good, it's created. I'm going to assign this. When the first scope dies, this shared entity dies. However, you can see that it hasn't destroyed my entity yet, it hasn't deleted it, because E0 is still alive and holding a reference to that entity. Now when I hit F10, that's when it dies. When all the references are gone, when all of the stack allocated kind of objects that keep track of all the shared pointers, when they die, when they get freed from memory, all of them, that's when your underlying entity gets deleted. All right, and finally there's something else that you can use with shared pointer called a weak pointer. And what you can do with that is just declare it like it was anything else and kind of give it the value of a shared entity. And what this does is kind of the same as if you were to copy that shared entity and increase the ref count, except it doesn't increase the ref count. When you assign a shared pointer to another shared pointer, thus copying it, it will increase the ref count, but when you assign a shared pointer to a weak pointer, it won't increase the ref count. So this is great for if you kind of don't want to take ownership of the entity. Like you might be storing a list of entities and you don't really care if they're valid or not, but you just want to store like a reference to them, right? With weak pointer, you can kind of ask it, hey, is this still even alive? And if it is, you can do whatever you need to do, but it won't keep it alive because it doesn't actually increase the ref count. I mean, if I was to actually replace this shared entity with a weak pointer, and then basically do the exact same thing that I did before, then the entity will get created here, it'll get assigned to the shared entity, but when I exit the first scope, that is when it gets destroyed. So this weak pointer is now pointing to an invalid entity. However, you can ask a weak pointer, are you expired? Are you still valid? So that's pretty much smart pointers. Now, as for when you should use them, you should probably try and use them all the time. If I'm being completely honest, they automate your memory management, they get rid of, they prevent you from accidentally leaking memory by forgetting to call delete. They're really quite useful. Shared pointer specifically has a bit of an overhead because of its reference counting systems, but then again, a lot of people who tend to write their own memory management systems tend to have a bit of an overhead as well. So it's a very delicate topic because you have this new breed of C++ programmers now who only use these kind of features, and then you have like the old school people who use new and delete. I'm kind of a bit of both because there is a time where you want to use unique pointer or shared pointer perhaps, but there's also a time where you need new and delete. So don't think that this has completely replaced new and delete. In my opinion, it has absolutely not replaced new and delete. It's just something that you should probably do when you just need to declare a heap allocated object and you don't particularly want to tidy up after yourself because you don't need to kind of explicitly call delete or explicitly manage that memory. In those cases, you should be using smart pointers. Use unique pointer whenever you can because it has a lower overhead, but if you absolutely need to share between objects or you just can't use a unique pointer, then use a shared pointer. But definitely go in that order first. Unique pointer first preference, shared pointer second preference. Hope you guys enjoyed this video. If you did, you can hit that like button. I know YouTube's changed. I said it was like I said it was there last time, but now it's like in the middle. It's like here or something. I don't know. Anyway, you can click that like button if you enjoyed this video. Leave any suggestions you have for future videos and all that in the comment section below, as well as any questions you may have. I have a Discord server where you can also ask questions, link in the description below. And if you really like this video and you like this series and you want to support it and you want to see more videos, then you can go to patreon.com/thecherno, pick up some sweet rewards by helping to support this series. I will see you guys next time. Goodbye.
I didn't really learn too much from that. I was kind of hoping for something a bit deeper, but it's aight. Something casual.
Back to the task at hand. Okay.
Three input lookup table. SRAM cell. CY and X control these multiplexers to produce F. Okay. Structure of the lookup table. In Xilinx FPGAs. It's patented. Frequency of rewriting is low. Area is more important. Five transistor SRAM cell. So address, data. This is a bit low level for me. So we're gonna skim. Is this? It's fine. It's also a remute. Yeah, right. Remute that. Yeah, not too bothered here. I'm surprised this is the suggested textbook, as this is not content in the class, nor based on what I've heard is the next chapter. We're talking about the internal representation and the trade-offs between different implementations of lookup tables. This is really not our domain, interestingly. Basic logic, so you have S, presumably a state, and then past transistor logic. Instead of using multiplexers, we use some kind of lower level transistor thingy. Okay. AC2 on FPGA. You got 2 input, 1 output muxes, 1 OR gate, NAND, and or NOR. So in a 2-1 mux, you can do some functions. Not too bothered by this. This is really not our domain. Mux type logic cells. Okay, so a quick Piazza check. Chapter 3. We're a fourth of the way done, and it's been 2 hours, but I was also messing around, so we're okay on time. Okay. Adaptive LUTs with more inputs and dedicated carry logics. Macro modules like DSP blocks, hardcore processors, and embedded memory. POL and DOL to deliver clock signals are introduced. Treats most of the FPGA components with examples of real devices. Logic block, 3 basic components: programmable logic element, programmable element, programmable interconnect, programmable logic element expresses the logic function of programmable element internal interface. Loading element connects different parts, or also different digital signal processing units, and embedded memory to increase the calculation ability, and phase lock looped or delay lock loop, yeah, to write a clock network. Routing channel, memory block, soft logic, multiplexers, and these kind of wrap themselves a bit as logic blocks. Sorry, logic blocks wrap themselves within logic tiles when provided with their adjacent routing channels in the context in their switch block. Okay, I want to know the principles more than the definitions. So yeah, back to the island style. That's been covered. 2D array. Multiplier and memory blocks for specific usages are hard logic. Functions implemented with logic blocks are soft logic. Logic blocks are named differently. CLB in Xilinx, logic array block in Altera/Intel. Similar since commercial FPGAs use LUT. So, although there was a logic block consisting of only LUTs in the early stages, recently they have basic logic elements. LUT flip-flop selector. M0 selector controls whether the value of the LUT or the one in the flip-flop is outputted. There are several trade-offs between area and delay. Area efficiency. How efficiently a logic block is used when a circuit is implemented on the FPGA. The area efficiency is high when logic blocks are used without arrays. Following trade-offs: as functions per logic block increase, the number of logic blocks required to implement the desired circuit decreases. Indeed, but as the area of the logic block increase, the area per logical tile increase. So more functions require more area. The number of LUT inputs is one of the most important factors in determining the structure. A k-input LUT can express all k-input truth tables. As the input size of the LUT increases, the total number of logical blocks decreases. On the other hand, as a k-input LUT needs 2 to the k configuration memory bits, this area of the logic block increases. Furthermore, as the number of input-output pins of the logic block increases, the area of the routing part increases. That's kind of a lot. Let me reread that. The number of LUT inputs is one of the most important factors when determining the structure of a logic block. A k-input LUT can express all k-input truth tables. As the input size of the LUT increases, the total number of logical blocks decreases. On the other hand, as a k-input LUT needs 2 to the k configuration memory bits. Okay, the area of the logic block, yeah. Furthermore, as the number of input-output pins of the logic block increases, the routing part increases, and the area increases, and so there's an area trade-off. And talking about speed, as functions per logical block increases, the number of logical stages, aka logical depth, decreases. Functions per logical block increases. Number of logical stages decreases. Logical stages. I'm uncertain what is a logical stage. The internal delay of logic blocks increases, indeed. Number of logical... Okay, so it's... Should have just continued reading. The number of logical stages is the number of logical blocks existing on the critical path. And so more functions within them decreases the amount of logical stages. Yeah, I believe that. The number of logic stages is the number of logic blocks existing on the critical path, which is determined at TEC mapping. When the number of logic stages is small, the amount of traffic through the external net routing track is reduced, which is effective for high-speed operations. Meanwhile, as the function of the logical block increases, the internal delay increases, and there is a possibility that the effect of reducing the number of stages may be reduced. Meanwhile, as the function of the logical block increases, the internal delay... As the function increases, the delay increases, and there's a possibility that the effect of reducing the number of stages may be reduced. Yeah. They're saying that as you increase the amount of functionality within a logic block, the amount of consecutive logical blocks needed to be effectively like pipelined to implement a certain circuit is reduced, but by having more functionality within each logical block, the propagation delay within the logical block is increased. And so the fruit of you reducing the number of stages may be diminished by the increase of the propagation delay by
implementing more functionality within each. Okay. And what is this table here? So it's kind of like the trade-offs of area and delay. And you find some nice middle grounds around like 5 to 6. That's interesting, actually. So this, I guess, this kind of goes back to modeling 7 LUT inputs as some combination of like 2 6 inputs. So yeah, that makes sense in hindsight if you're reading this. Summarizing the above, if the input side of a LUT is large, the number of logic stages is reduced, resulting in higher operational speed. However, when implementing a logic function with less than k inputs, the area efficiency is reduced. On the other hand, if the input size of the LUT is small, the number of logical stages increases. Yeah. If the input, yeah, okay. The number of logic stages increases and the operational speed is degraded, but the area efficiency improves. In this fashion, the input size of the LUT is closely related to the area and delay of the FPGA. Yeah, okay. The following elements have a great influence on the logic block architectural exploration. The number of LUT inputs, area and delay, process technology. An architecture evaluation of logic blocks has been studied since the 1990s. 4 input was the most efficient. I feel like 5 is looking kind of nice. 5 is looking nice. 6 is looking nice. Curious what the just differences. Kind of curious there. 4 input was the most efficient. Even commercial FPGAs, 4 input LUTs were used until the release of the Xilinx Vertex 4 and the Altera Stratix. Meanwhile, another architecture evaluation was performed using the CMOS 0.18 picometer symbol. Mu meters. What is that? Micrometers. Okay. Yeah, so I don't really care about that. Minimum width transistor. SPICE simulations. So this is good results are obtained in terms of area and device. This is probably the updated one. Yeah, figure 3.3. Is that this? Yeah, okay. Recent commercial FPGAs tend to employ 6 input LUTs. Okay. That's kind of cool. 6 input LUTs. Shout out 6 input LUTs. For the purpose of improving the performance of the arithmetic operation, a dedicated carry logic circuit is included in the logic block of commercial FPGAs. That's kind of interesting because when I was reading that other book, talking about all the different, even like adder algorithms, like the carry adder and the ripple carry adder and all that, or the ripple carry adder and the merge adder or some junk. So I don't think that really covered dedicated carry logic, interestingly. In fact, arithmetic operations can be implemented in LUTs, but using dedicated carry logic is more effective in both degree of integration and operational speed. Figure 3.4 shows 2 types of 2 full adders are connected with dedicated carry logic. The carry in of FA0 is going into the adjacent logic block. This path is called a high-speed carry chain path, enabling high-speed carry signal propagation in arithmetic operations. In the arithmetic operation mode, shown in Fig 3.4, so we'll get to that. Each circuit sums the outputs of 2 4 LUTs. So let's just skip to that. So arithmetic mode, you have 2 4 LUTs where you're piping their outputs into a carry in. And we are asserting 2 flip-flops. So we have like out and the previous out or something. I'm unsure as to the utility of that, but let's just consider it that abstracted out and look at the contrast with shared arith. On the other hand, in the shared computation mode of figure 3.4b, 3 input 2-bit additions can be executed by calculating a sum with LUTs. This is used to obtain the sum of partial products of the multiplier within an addition tree. Figure 3.5 shows the dedicated carry logic of a Xilinx FPGA. Shout out to one on my PC and the one on my drawer. In this FPGA, full adders are not provided as dedicated circuits. Okay, that probably makes sense. I guess that's why I haven't read about it. In this FPGA, full adders are not provided as dedicated circuits in the addition
Oh, okay, that is the carry gen circuit, so never mind. And the addition is realized by combining the LUT and the carry generation circuit. The addition sum of the full adder is generated by two input XORs, and the carry out is generated by one XOR and one MUX. So I can't envision that off the top, but we'll see in a second. The XOR of the preceding stage is implemented by a LUT, and the exclusive circuit. And the exclusive circuit is prepared for the MUX and XOR of the latter stage. The XOR of the preceding stage. So we'll just look at the figure. Multi-bit adders is possible since the carry signal is connected to the nadir, so you can chain them. Okay. So let's look at this. Truth table of the full adder. This is the truth table of a full adder. The dedicated carry logic. Cout. So why are there 3 inputs to a 2-bit MUX? Or that Cout is an output. But Cn is going into it. So the output is also coming out, wrapping around to in 1, sorry. So it's using a MUX like an adder, like a 1-bit adder. XOR. So if they're not the same, you'll have no carry out. If it's 0, 0, carry out is the XOR of N0 and N1. So it's only out if they're different. True, there's only a carry out if they're different. What about carry in? Sum is carry in. So what should first go to the truth table and then you go to this, I think is a better tag. In 0 0. In sum 1. In 1 0 0 1. 0 1 1 1 0. 1 0 0 0 1. 1 0 1 1 0. 1 1 0 1 0. 1 1 1 1 1. So sum is asserted. Looks like Cout is a bit easier. When is Cout true? Cout is true when 2 or more of the inputs are true. 2 or more of the 3 are true. So that's why you have Cn in 1 and in 0. I'm just a bit confused why that's a MUX. Carry out as a MUX. Dude, I'm not talking about freaking Uber Eats. Spawn moonlight. This is not super obvious to me. What is this multiplexer? Oh, the 0 and 1 are not constants. Or is this like the nth? What are the 0 and 1 here? You're using the XOR to select between N1 and Cn, yeah? So N1 is 0. Cn is Cn. And 0, when this is 0, it'll select 0, and this is 1. Okay, that's what the 0 and 1 is. These are like the indices. 1 0. So let's just try it. 0. This is a 1, so this will be 0. As well this. Let's look at like the 1 0 0. Okay, so 1. So this is 1 0. Cn is 0. So you need one where this is high So let's look at this case, 101. 101. C out is 1. Sum is 0. 110. C in is 0. 1. So 1, 1, 0. C in is 0. C out is 1. I'm confused how 110 is 10 in this, because the 0th bit, 0 is going to select Cn. Cn is 0. From me I'm gonna just move on. Sometimes you gotta just move on. Logic cluster. To increase the number of functions in a logic block without increasing the number of let inputs, cluster-based logic blocks, also called logical clusters, grouping multiple BLEs. Bluetooth low energy basic logic element. Full crossbar part is called a local connection block or local interconnect, and multiple basic logical elements are locally interconnected with a logical cluster. They have the following features. Since the local wiring in the logic cluster is composed of hard wires, it is faster than the global wiring outside of it. The parasitic capacitance of the local wiring is small when compared with the one of the global wiring. Therefore, using local wiring is effective to reduce the power consumption. You have 10 inputs. Sending 4 to each 4 basic logical elements, which are outputting their own stuff. They can share input signals, reducing the number of switches, reducing area, increasing functions. So using this, you can decrease the area, the increase in the area with respect to k, which is originally exponentially, to just be quadratically, because some of the functions will often share signals. Okay. That's good to know. N equal to 3 to 10 and k equal to 4 to 6. So that's n general inputs and k. No, k inputs. N blocks. Interesting. Adaptive LUT. High implementation efficiency. Commercial FPGAs logic blocks have been evolving in recent years. 6 LUT. So you have 6 LUT, 5 LUT, 4 LUT, 3 LUT, 2 LUT. It's interesting that it's a bunch of 6 LUT and then decreasing, but no like small amount of 7 LUT. Kind of interesting. 45% of the total logic function was mapped to the 6 input. This is like they're all 6 input. How much are being used? Yeah. Adaptive LUTs. You can divide LUTs to implement multiple logics. It's kind of nifty. 388 shows an example of an adaptive LUT-based logical block. Inputs and outputs is 40 and 20, including C and C out. Respectively, the number of clusters is 10. The local connection block is a full crossbar of 60/60, and its inputs include the feedback outputs of each adaptive logic element. The adaptive logic element includes 2 output adaptive LUTs and flip-flops. It has two 5 LUTs sharing all inputs, and this is shown in figure 3AB. So looking at the adaptive LUT-based logical block, 40 general inputs going into a 60 by 60 crossbar. So we have 40 external inputs plus 20 feedback lines to get 60 BLE inputs, sending 6 inputs to each of 10 adaptive logical elements, with carry-ins piping between each of them, making 2-bit outputs and 2-bit feedback lines. Carry out. So we're looking at it like a bit zoomed now. We have all these 5 LUTs. These adaptive LEDs are 5 LUTs. Sorry, this is something else. Similar to something else. So you have these same inputs going to each of 2 5 LUTs, carry in and out between them. So is this a full, what is this? 38B. What is 38B? I guess it doesn't have an explicit function. Excuse me. But it also has a flip-flop and a mux to assert 2 outs, okay. And you have an arithmetic mode where you have a dedicated carry circuit and a mux. I kind of talked about that. An ALE can operate as two. Oh, okay. So this is to chain. This is to act as a 6-input LUT. Okay. Area efficiency is increased by dividing the 6th LUT into small LUTs and implementing multiple small functions when the circuit resources at the 6th LUT. However, increasing the number of inputs and outputs leads to an increase in the area of the wiring part. True. For this reason, the number of logical block inputs is suppressed by input sharing. There's patents. Since 04, when adaptive LUTs appeared. And that's kind of the latest one we get. And so this has some, so we're skipping that, just FPGA specific implementation of that, that's fine. The routing structure of an FPGA can be roughly classified into the full crossbar type, the one-dimensional array type, and the 2D array type, or the island style, and the hierarchical type. These are classified according to how the logical block and the IO block are connected, so-called a connection topology. All of them are composed of wiring tracks and programmable switches, and the routing paths are determined according to the values of the configuration memory bits. The full crossbar type shown in figure 310A has a structure that always inputs the external input and the feedback. Has a structure that always inputs the external input. So this is the output of the crossbar. And the feedback output of the logical block. This routing structure was commonly seen in programmable array logic devices with a programmable and a plane. Since current FPGAs have enormous logic blocks, that's inefficient. The one-dimensional array type has a structure in which logic blocks are in a column, and the routing channels are provided in the row direction. So let's look at this. Full crossbar type, all of these inputs with all of these feedbacks are explicit. The one-dimensional type has adjacent logical blocks connected in columns, and then the columns are connected in rows. The two-dimensional type, island style, has everything connected, and the hierarchical type has this kind of like zooming logical blocks, group of logical blocks, okay? Channels are connected by feed-through wiring, which corresponds to some particular FPGA. One-dimensional array increases the number of switches. I mean, it looks like this has the most amount of switches. Or, I mean, I guess these aren't switches as much as wires, right? Anti-fuse type switches, because their areas either small or almost non-existent. Wait. SRAM switches are the mainstream. One-dimensional and full crossbar aren't adopted. So hierarchical. So these are apparently more efficient. Like, how many lines is this? 4, 4, 4. 3, 3, 3, 3. And less logical blocks. I guess there's the same amount if this is infinitely long. You're just missing however many this is. Like the amount of columns. The difference in the amount of columns minus 1 or something. dimensional, one-dimensional array type, full crossbar type. But either way, I don't really care to do much besides derive that the hierarchical and island style / two-dimensional are particularly useful. Global routing architecture. The routing structure of an FPGA is classified into global and local routing architectures. Global routing architecture is decided from a meta viewpoint that does not consider switchable details, such as connections between logical blocks and the number of tracks per wiring channel. On the other hand, local routing architecture includes detailed connections, such as switch arrangement between logic block and the routing channel. All four are global routing. So looking at hierarchical types, Altera Flex 10K, Apex, Apex 2 have a hierarchical routing architecture. Interesting. UCB HSRA, high-speed hierarchical synchronous reconfigurable array. So I don't care too much about that. Here's your island style, and you have this hierarchical style. So for the above reasons, a hierarchical routing architecture was effective in older processes where the gate delay was more dominant than the routing delay. Okay, island style, most FPGAs in recent years, vertical and horizontal, 2-point or 4-point, detailed routing architecture, switch arrangement between logic blocks and the length of the wire segment are determined. W, so let's look at this. Programmable routing switch here. Routing blocks, switch blocks, spreading track, short wire segment, long wire segments. So these can be cut, intersected by logic block spreads. W denotes the amount of tracks per channel, and there are several wire segment links. There are two types of connection blocks, one for input and one for output. So you have input in this axis, output in this axis, and they switch in between the axes. Okay. You have a flexibility. The wiring elements composed of a connection block and a switch block have a very large influence on the area and the circuit delay. Its area is large. Wiring delay is dominant over the gate delay. When deciding the detailed routing architecture, it is necessary to consider the relationship between the logic blocks and the wire channels, the wiring segment length and its ratio, and the transistor level circuit of the routing switch. However, there is a complicated trade-off between routing flexibility and performance. Increasing the number of switches can emphasize flexibility, but also increases the area and delay. True. On the other hand, if the number of switches is reduced, routing resources become insufficient, rendering routing impossible. The routing architecture is considered based in routing architecture is determined considering the balanced use of pass transistors and tri-state buffers. So you have all these different length of wires that it's almost like you're playing Crossy Road and you're going across a river full of logs. You gotta like time what logs you're trying to get to. That was horrible. I'm just gonna shut up, okay? So you benchmark it to determine the wire lengths. You can have bidirectional wiring or unidirectional wiring, and there's trade-offs. Unidirectional wiring capacity is small, there's a trade-off. Shifting to unidirectional, interesting. See, there's no utility in memorizing this. It's just good to know that they're derived by benchmarking and that there are different types and presumably trade-offs between them. Switch block topology. So let me take a second to consider if I'm doing laundry today. So I'll probably do laundry tomorrow morning instead. Do sheets and loads. Laundry there. I'm not gonna have time. 30 minutes plus the hour, and then I gotta go to stats lecture. Frick. Huh. Problem is, all my classes are at 9:30, and if I wake up at 7:30, I'm never gonna have time to do laundry. I'm gonna be speed running laundry, so I probably just do it right now. Give me an hour laundry buffer at the end. Spamming. I just won't read Kubernetes tonight. Because I just read all this, and that gives me 3.5 more hours for this. And tomorrow morning. So I was planning to read a lot of Linux kernel development but tomorrow morning I try to do my homework or something in that. We do compile. Let me add for tomorrow. Compiler is worksheet 1. I'll come back, do a short lunch for OS. Leave after I eat. Then I'll have an hour 45 in here. I can work on linear homework 1. Spamina. So I'll work on linear homework 1. So compilers, I want to finish comp worksheet 1. I want to finish sec lin alg homework 1. So after OS, I'll come back sec lin alg homework 1. It took me an hour 30. I haven't looked at the homework. Give myself 2 hours. What else should I do tomorrow? I'm gonna work on the compilers, extra credits. I could do processor design lab 0. I'll do that. So linear. And proc des lab 0. Is that what it is? Lab 0? Lab 0, yeah, let's do that. And then by Saturday, I'd like to finish the bonus project, the comp branch. Do that there. I'd also like to do lab 1. That'll be Proctes. Lab 1. And I'd like to do, what is it? It is, it is compilers. Stats homework 1 is due on Tuesday. Let's make that Sunday. Stats homework 1 on Sunday. Also on Saturday, I'll do, what was the other thing? Что-то было, что домашнее задание в компилерах первого, да? Ебать. Yeah, I think it was compilers homework 1, yeah? Compilers homework 1. Yeah, I was tweaking. So, this week, probably won't finish Linux kernel development there. Just gonna switch my setup a bit. Just gonna remove this. And so second Linux homework 1, 2 hours there, and processor design 0 probably take me 2 hours. And then I might do a stream. That'll give me 2 hours and 30 minutes to do a stream. What should I stream? I've done compilers worksheet 1 in the morning, laundry. I was doing that tonight. So I could stream. I can also just publicize this. I don't really care if people see what I do. I could pick up a new Gleam issue. Should probably work on Punt Engine, if I'm being honest. Yeah, I'll probably work on Punt Engine. In the following command. I think this is a skill issue. And maybe not. This is intentional. If your manifest toml is corrupt, look at its manifest toml. CD. Where'd I put that? Cat. Bro, I feel like your manifest toml is probably corrupt. Okay. Generate dynamic decoder. Hello? Let me scroll. Oh my god, Chromium is so shite. Hello? Can I please scroll? What is going on? That's why I use Vimium. Code action to destructure a function argument. Wait, that's a thing? Oh, that's a cursor. I'm tweaking. Destructure. Oh, yeah. That is cute. That's real cute. That's kind of nice. That looks kind of hard though, but I do like that. Let me scroll. Oh my. Oh, that's eight. That's eight. Oh, worksheet one is due tonight. You're tweaking, dude. Nah, you're tweaking, bro. I said it was due yesterday. I said it was due tomorrow. All right. So that doesn't still didn't answer the question. What would I stream? I'll start stream Punt Engine. Stream order book. ISA, sure. And so I have laundry buffer, and I'll leave 30 minutes for the compilers worksheet. Come on, bro. Hours worksheet 1. Practice 5.0. Homework 1. Then ouch. Just make this consistent. Sec. Ouch. Sheets. I'll do that tonight. Laundry, I'm doing that tonight. Practice. Okay. Ladna. Okay, back to this. Switch box topology. Let me get a bath. Let me start my laundry. Okay. Is this how much is left in chapter 3? Considerable amount. So we're gonna pause here for a second. We're gonna go to temporarily gone. I'm gonna go here. I'm just gonna go here.
All right, 22 minutes until I get to go get my laundry. And also, I just realized the Gleam issue that I was roasting somebody for having was actually valid, and I'm just dumb. So it's kind of dope. Switch block is located at the intersection of the wiring channels in the horizontal direction and the vertical direction. Disjoint type, universal type, and Wilton type. So these are all external things. It's a bit inconvenient. The Wilton type forms a closed circuit by several switch blocks by passing through a clockwise or counterclockwise path. By using this feature, it was shown that the efficiency of manufacturing tests. By using this feature, it was shown that the efficiency of manufacturing test of FPGA. So the test they use to determine the efficiency of manufacturing can be improved, I think is what this is. I'm not too worried about that. Especially in unidirectional wiring, multiple input multiplexers exist everywhere on routing elements. Sorry. Multi-input multiplexers have large prop delays. Circuit structure is important. 9 normal inputs and a high-speed input. Circuit delay can be improved by 3% without increasing the area. In this manner, the program switch for the routing element has a great importance in reducing the path delay if the configuration memory increase is allowed. On the other hand, a LUT is often composed of pass transistors in a tree structure. Feeder placement, transistor sizing of multiplexer and wiring is undergoing. To reduce the circuit delay of unidirectional wiring, CMOS inverters are usually used for the routing driver of FPGAs, and 37 has reported that the number of drivers has better delay characteristics in odd number stages than in even number stages. Connection block. The connection block has a role of connecting the input and output of routing channel, and the logic block, which is also composed of programmable switches. Like the logical connection block, CB has a local trade-off between the number of switches and the flexibility of routing, particularly since the routing channel width is very large. If it is simply composed of a full crossbar, the area becomes a problem. For this reason, sparse crossbars are used in CB. Figure 319 shows an example of a CB composed of spaced crossbars. So this is just not relevant to the class or me. So skip. IO block and IO elements is a dedicated IO module between an IO pad and a logic block. Arranged along the periphery of a chip. Power supply, clock, user IO. Be latched. Pull down and pull up resistors at the output part. Output of the device can be clamped to 0 or 1. An output buffer within a neighbor signal. But output has a flip-flop, so latency adjustment is possible. Slew rate can be controlled. Input buffer has a threshold of time to life. Is that what that is? Or CMOS? Transistor logic. I'm cooked. Yeah, I know nothing about that, so forget it.
Commercial FPGA has various interfaces for providing different output center voltage, electrical matching, and I/O. Many FPGAs also support differential signals, low voltage differential signaling, in order to treat high-speed signals, and are equipped with a reference voltage for handling different voltages and a clamp diode for handling a specific high voltage. I/O bank method. DSP box. See, I've read about these for DSP. You can have dedicated DSP blocks. So we got a Mac ALU. Pre-adder going into a multiplier, going into a accumulator, pattern detector. Granularity / bit width of dedicated hardware box affects the implementation efficiency. Wiring delays if they're smaller and you need more. Port area efficiency if they're huge and you don't use a lot. SIMD. You can do two 24-bit additions or four 12-bit additions in parallel. It's kind of cool. Scientific computing. Use IP tools. By following HDL coding styles from FPGA vendors, your synthesis tool can infer usage of DSP blocks. I'm going to instantiate the primitives. Hard macros. When large-scale FPGAs became available with the improvement of semiconductor integration, degree system on FPGA and a whole complex digital system is implemented on a single FPGA chip. Major FPGA applications. Hard macros are on-chip dedicated hardware circuits. DSP blocks are hard macros. Hardware multipliers are hard macros. PCIe Express interface, got that. DRAM interface, got that. Analog to digital converters don't have that. High-speed clock signals are increasingly needed, along with expanding demands for high-performance peripheral devices. Unlike the logic blocks and DSP blocks, only a small number of interface circuits are provided as hard macros for each FPGA. The layouts of user logic connected to these hard macros require close attention, so it's unexpected logical errors decrease performance. When FPGA users wish to implement a whole complex digital system on a chip, a microprocessor is often an essential component. Since any logic circuit can be implemented on FPGA, the users can also implement microprocessors on the programmable fabric of the SPA. They are called software processors. There's a lot of IP. There's a lot of open source ones. While software processors have the merit of flexibility, dedicated processors implemented on chip hard macros are advantageous in terms of performance. Xilinx has them. I believe this FPGA right here. If I'm not mistaken. In the Zybo Z7, yeah? If I'm not capping. So I have the heatsink. This might not actually have one. Yeah, I actually don't think it has one. Rip. Never mind. That was false. Power PC Xilinx. Yeah, so they have some ARM cores. And so, what are we looking at here? The ZenQ 7000. You got your I/O. Got flash memory controller and the SRAM. DRAM controller. Got programmable logic all around the perimeter. And you got your I/O interface. PCIe on the high speed. Another I/O interface on the side. Then on the actual FPGA fabric, you have some 2 floating point engines, 2 hard processors, cache, some on-chip memory. That's kind of dope. They can run Linux. Embedded memory. Difficult to store a large amount of data, and so you can have embedded memory DRAMs and VRAMs and SRAMs. TIPA. FPGA architectures, which are based on logic blocks, consisting of LUTs and flip-flops. Flip-flops in the logic blocks for the only memory elements available. Difficult. Am I capping or did I just read? Yeah, I just read that. I messed up. On-chip memory boxes, hard macros. Xilinx, you got block RAMs. Got a few of those. Memory access port of the block RAM, control signals, A port and B port. Not only a single port memory, but also dual port. FIFO, yep. Sending data between submodules. Must be synchronized with clock signals. Memory using LUTs. You can use logic blocks. So by using LUTs as memory elements, you can increase the chip capacity while increasing hardware utilization. So this is a BRAM. It's called distributed RAM. Can't do it with all of them. You need slicems. It's recommended for very small. Embedded memory. IP generation tool is RAM, ROM, dual port RAM, FIFO. DRAM or distributed RAM. You can use HDL code to infer it. DRAM in computer systems cannot be configured inside FPGAs. Large bandwidth. Efficient application mapping. Circuit information. Used to configure circuits is called a bitstream or configuration data. Takes a few times to fill in all the truth tables. Takes some time to fill in all the truth tables. Different memory types. You need to store configuration data inside the chip in some way, and the storage is usually called configuration memory. The configuration memory is classified into the following three types depending on the device technologies used. SRAM is a rewritable volatile memory. While FPGAs in this type can be configured many times, it'll disappear when the power supply goes off. Flash memory is non-volatile. Write speed is slower. Can be effectively reconfigured many times. Anti-fuse is an insulator at first, but applying high voltage makes it a conductor. Using this property, configuration data can be kept like non-volatile memory. Once it's a conductor, it cannot be an insulator again. It's one time. JTAG interface. SRAM FPGAs are configured from external configuration data memory when the power is turned on. So you can have active access or passive. Joint test action group interface. Captured into unused embedded memory. Read back through the JTAG interface. POL and DOL. Since FPGAs can configure various circuits whose operation frequencies are naturally varied depending on critical paths, it is convenient that a clock signal with various frequencies can be generated and used inside the FPGA. With circuits configured on the FPGA can communicate with external systems, it is desired that the clock signal, which is in phase with the external clock, is generated. In addition, when the FPGA is connected with multiple peripheral devices, multiple clock signals that have different frequencies and phases are needed according to each interface standard. Thus, recent commercial FPGAs provided on-chip programmable phase lock loop mechanisms that various clock signals can be effectively used based on an external given reference clock. Reference clock, phase frequency detector, low pass filter, VCO, output clock, feedback. We got 5 minutes. Let's finish chapter 3 real quick. Basic structure and operating principle of phase lock loop. It's a voltage controlled oscillator. Feedback structure. Reference clock output. Input from the outside and the clock generated by the VCO, which is a voltage controlled oscillator, are compared by a phase frequency detector. When the comparison results show that there is no difference between the two clock signals, the same applied voltage to the VCO can be maintained. If the frequency of VCO is higher or lower than the reference clock, the voltage of the VCO needs to be decreased or increased. Generally, a charge pump circuit is used to translate the comparison results into such an analog voltage signal. Although it seems that this analog voltage signal can be directly used to regulate the VCO clock, it will make the system unusable. Thus, a low-pass filter is provided in front of the VCO to cut off high-frequency components. In this way, the clock signal that has the same frequency and the same phase with the external reference clock is generated in a stable manner. This operating principle, illustrated in figure 325, is basically implemented as an analog circuit. Typical POL block. That was basic. Can only be the same as the reference. You often need different frequencies, so you can add programmable clock dividers. So you have a bunch of so when you have the feedback, you also split out the outputs into all these different dividers, and you have a reference clock divider. So you just keep dividing it by different dividends, yeah, and just getting your output as desired. Fair enough. The reference clock is given to the divider in front of the phase frequency detector. When this dividing rate is n, the target frequency becomes 1 over n of the reference frequency. I got 40 seconds. 1 over n when it's m. 1 over whatever, sure. 3, 12, 3.
The ghost pop tape is over. Flexibility and restriction of PLL blocks. Let me get a. Sorry, was muted. And by water, I mean decaf tea. Shout out Tea Pigs, actually. They're kind of expensive, like Whole Foods BS. But I actually like it. Tea Pigs cold brew. Tea Pigs cold brew is nice. $60 for 46. That sounds kind of bad for tea bags, but it's also not dust. And you can get like 5 glasses out of one. I'll get one of the black currant and raspberry. They got a gingerbread? That's crazy. Gingerbread? That's wild. I'm getting a gingerbread, homie. I'm getting a lychee and rose too, bruh. They're kind of clean with it. Kind of nice with it. All right, I'm getting $46 on them though.
All right. Had some book cooking. Blah. Had some bookkeeping to do. Let's get back to this. So there's clock configuration GUIs. In a delay linked. Unless it said combined block DLL and dynamically linked library. That's a delay locked loop, not a dynamically linked loop nor a delay linked library. So you don't use a VCO. Clock and DSQ. Phase locked loops are more flexible and they're more commonly used. Design tools. So, halfway done as expected. And the last subject is how to use the hard macro processor on recent system on chip style FPGAs. Designers have to read large amounts of documents. Facts. All right. I'm gonna check out dude's office hours in a second. Design flow. Where's the start point of this? IP and behavioral description, block diagrams, store. So I guess you have all of these. Logic synthesis, net list, place and route configuration data, download, FPGA, prototyping. So this is a Microsoft. Nah, this arrow is the most Microsoft Illustrator thing I've ever seen. Design flow by hardware description language. Projects have constraint files. Just a bunch of junk. Pin assignment clocks. Excuse me. Source code registration. A tree of your sources. Top module, everything else. Yeah. IP and registration of source code for simulation. What was the difference? Like your system Verilog. Your okay. It's like your test bench. Yeah, that's John. Logic synthesis and technology mapping. Product of logic synthesis is referred to as a netlist. Programmable logic elements and lookup tables. So yeah, some intermediate wires, registers, etc. might disappear in the resulting netlist. Show. Termination time and breakpoints. You simulate at different levels. I know that. It's a BitRAM, SRAM object file or others. Several methods directly write bits via the JTAG. Write to a non-volatile memory card, USB. So joint test action group is the standard protocol for programming PCBs. The designer connects a board to a PC where you run USB cable. Configuration data is directly written to the target FPGA device using the program tool. This is an easy and small way, but the program circuit vanishes on power off and reset. So this is the configuration data. Example of the generation process of configuration data from place and route. So yeah, FPGA configuration methods. So you got the PC SD card, you got the USB JTAG via USB to non-volatile memory. Or you can just put it directly on it. No designer might use it. Flash memory. Passive and active. MCS program object files. JTAG. More complicated. A very dumbed down FPGA with dev board.
Alright. Frick, dude. Alright, keep going. I got OEDs. Under receiver, data valid ready stream type, data address write enable, data address read enable, memory bus type. 3 types of interface. Here, he's got some IP. Understand. Each chapter of this book was written independently.
kind of freaking useless. Alright, the end of that was kind of useless. Design methodology. So we'll have design methodology, then hardware algorithms. That'll be useful. And that's quite a long chapter as well. Then we'll have programmable logic devices and practical applications. Then we'll have advanced devices and architectures. So, So, in the rest of this, there's probably about 10 pages that are pictures. So there's about 100 pages left.
Design methodology.
Turn my monitor brightness down when it's getting later.
So, technology mapping for general K input LUT, K LUT consists of the two following steps. Decomposition process. Since the actual gate level netlist is represented by a Boolean network, each node is disassembled until it becomes less than the input number K of the LUT. Covering process. The Boolean network decomposed in step 1 is converted to reduce the number of inputs based on appropriate criteria, so the level nodes are converted with K LUT. Depth optimal solution of the covering problem of step 2 with polynomial computation time. Convert it to a directed acyclic graph. Primary input, primary output, focusing on the PO on the right side of C. The nodes related to the PO up to the PI are surrounded by the dotted line. The selection represents the mapping range of the PO. Next, D illustrates labeling and cutting. Labels are attached in the topological order from the PI, and the conditions are attached as follows. Set the label of PI to 0. Next, search the range that can be covered by the 3 LUT among the nodes that take PI inputs and put a cut in the input. The label calculation at this time adds its own number of label that is level 1 to the node with the largest label immediately after the cut.
Once the label of the node is calculated, we can calculate the labels of the nodes that are connected to the node that's calculated from the label. That calculated the label, sorry. If it's not yet determined, it should be done from the finalization of the label first. Gate level net list. A more abstract directed acyclic graph. Mapping the output range. Mapping the range for output T. Labeling and cut. So this is like the minimum depth. Or no, it's not the minimum depth. Mapping, so you go to the zeros, and these are 3 LUTs. Two. Three LUT, 3 LUT, 3 LUT, 3 LUT, 3 LUT, 3 LUT, 3 LUT. Group multiple LUTs on a logic block. The delay inside a logic block and outside of it is very much different. Unused resources decreases of implementation efficiency. VPAC. Minimize the number of clusters, minimize inter-cluster connection. TV pack. It's timing driven.
What is and let, bro? Versatile place and route. Optimize placement by random placement and pair exchange method. Optimize placement by random placement and pair exchange. The cost is the sum of the length in the horizontal direction and the length in the vertical direction. The cost is small as the logic blocks gather. Okay. Excuse me. There's also one called timing driven router. It's an algorithm based on Pathfinder. It uses directed search for the net route search between source and sinks. So is this for uni? I guess it's not only for unidirectional wiring. Because it can kind of infer the directions that you're using. Using directed search, the cost of the between source and search location. The estimated cost between search location and sync. The predicted cost is the cost of delay when using the same kind of wire as the node in and connecting with the shortest distance. Routing to each net with minimum cost. Because wires that compete for multiple nets tend to be crowded, congestion costs are added to the evaluation values. If a net cannot be routed because of conflict, searching for the least cost path for each net is executed again. Since the wire cost has been updated since the last search, the route is possibly changed. Conflict decreases from last search due to route change. Yeah, that sounds freaking so time consuming. If conflict still exists, similarly add cost and search wiring route again. Execute this operation until there's no conflict. The placement and routing process is time consuming because it involves many optimization problems. In order to improve this practically, in order to improve the practicality, speeding up these processes is essential. In addition, it is necessary to cope with an architecture which makes it more functional, such as cluster structure of complicated logic blocks, dedicated circuit, dedicated wiring, and so on. In order to cope with such requirements, the VPR development team introduced device definitions based on XML and the VPR 6.0. That's Verilog routing project. And it's an open source FPGA development framework. Really. I think with hardware, like, my bad for saying like, coming from software, if you like compilers, find an open source compiler and contribute to it. If you like hardware, what do you even do, bruh? Low power design tools. In order to reduce the power consumption, it's necessary to lower the power supply voltage, the operating frequency, the load capacity, the activity. We focus on reducing the load capacity and the activity. SRAMs have large power consumption. EMAP. So it's really about optimizing the activity because the SRAM is already there. You don't want to decrease your clock. And you don't want to decrease the voltage. So that's what you have to work with. So we're looking at the same 3-input LUT. However, since the wiring with high switch activity value is outside the LUT, even though the delay performance is the same, the power consumption increases, yeah. Minimize duplication in nodes. You can duplicate for delay optimization, but this increases the nodes and power consumption. In EMAP, duplication of critical paths is allowed, but in other wiring, the duplication is suppressed. Also, the duplication of a node occurs when nodes with multiple fanouts are inside the cone. So EMAP adopts measures such as making nodes with multiple fanouts as root nodes. As a result, any increase of nodes is suppressed when compared to conventional flow map. Figure 511 shows an example of node duplication. Cutting is selected so that node 3 becomes the vertex of the cone. However, in figure 511b, it is in the middle. At the time of the cut selection, both are the same for the number of cuts and the number of LUT stages. But B, since the fanout of node 3 is 2, the duplication of the node results in the generation of a LUT. That is, the LUT increases by 1. EMAP suppresses this duplication of such nodes. So in activity-aware technology mapping, you got, these are like usage metrics. These are not. These are activity metrics. And so, looks like you get just as many LUTs, yeah? But their usage is higher, perhaps. 2, 2. If you look at this graph, 2, 1, 2, 3. 4, 1, 2. then you're grouping. So instead of grouping these into a LUT, you're grouping these with higher usage metrics into the LUT, and so the LUT shifts to the right. So you have the 2 and the 3, add to the 6 instead of the 0.1. And then the sum of the utilities of these is greater. 6, 1, 1, 3. This is like 1. Sorry, 8.8. PV pack, low power consumption clustering tool. Same method as EMAP to reduce the activity, considering the load pass capacity of the wiring existing inside and outside the BOE. The wiring outside the BOE has a large wiring length. In addition, since many transistors such as a connection block and a switching block are also connected, the capacity is generally large. It is more advantageous for power consumption to include wirings with higher activity as much as possible within the BOE. In this example, when the combination of clustering in Figure 512A and the clustering in Figure 512B are compared, the activity of the wiring connecting between clusters is lower, 0.1 in A, than in B, 0.4. Therefore, when the load capacities of the wirings between the clusters are the same, the power consumption of A is lower. Technology mapping considering fan-out. So these, now we're trying to optimize within the basic logic elements. 2, 5, then we have this grouping 0, 3, 4, 6, 1. Now we have 0 in its own LUT. Sorry, this is with considering fan-out. Without considering fan-out, we had 0 in its own LUT, 3 in its own LUT, and 3, 6 together. So we had 0. We had 2, 2 to 5. 3 was its own, so it went directly into 3, and the output of the 0 one went directly into 3 as well. 3 had its own, which made it a bit more pipelined. You got the 1, 4 over here. This is the 1. Even the 1, 4 is so... I'm a bit confused by that, but then it goes down to this, to the 6. Or is this the 4? Dun, dun, dun. Yeah, this is like the 6 or something. We're grouping the 1, 4 here. It's got 3 inputs and a 1 output, yeah. And then this has 2 and because we're grouping 3, 6. This is 3. This is 3, 6. Yeah. This takes from 3, 6 and 1, 4, and we grouped it with 3, so it has this duplicated. I can't tell which. I guess it's coming out of here. So that's the output of 3, and it also goes into here. Yeah, that's true. But with considering fan out, we save a LUT by not pipelining this, it appears. They were deduplicated. Yeah, they were deduplicated for efficiency, but we combined them. Okay, that's cool. The basic idea of PVPer, low power consumption, is similar to PTV pack and EMAP. However, since wiring with high activity cannot be hidden in placement and routing connection for such an edge to be as short as possible. When priority is given to the switching activity, there are cases where a signal line whose switching activity is low but its timing is critical may eventually be detoured and the delay may increase. Such a trade-off is adjusted with the weight parameter and the cost function to find the balance that minimizes the energy. Interesting. Activity measurement tool. As in previous mentioned tools, it is possible to reduce the power at the design tool level by considering the activity. Indeed. However, what is important here is how to accurately obtain the activity of each node. It's like the you want to have a scheduler that schedules all processes fairly. Oh, just let every process claim. It's, well, that's a bit different. It doesn't solve the problem inherently by just gauging things by their activity, because it's part of measure their activity. That's what I was trying to say with that. Wilton et al. Proposed a tool called ACE Activity Estimator for activity measurement. There are 2 ways to roughly calculate the activities. The first one is a dynamic method based on simulation, and the second is a static method stochastically obtained. Just stochastically. That's not what I was trying to see. Stochastically. Randomly. Okay. Pretty sure.
So here we have activity. So I'm first going to look at clustering without considering activity. Or let's look at this one first. So the difference here is that 2, 1, 2, 3, 0.1 into 3. So we brought one of the LUTs up. Okay, we brought a LUT up to a higher, to a parent. We've brought a LUT up to a parent BFL, BFE, BOE, BOE. We brought it up to a higher BOE. And how does that say power? Because the line between them is more used. Or it's less used. We pushed it down so that it's less used. Okay. Dynamic methods have higher precision, but they are time-consuming. Further accuracy is easily affected by the test pattern. On the other hand, the static method based on probability is low in accuracy and the execution speed is fast. Also, since the probabilistic method reacts sensitively to setting the transition probability of the input signal, the initial value is an important factor in determining the accuracy. ACE is a tool to statically analyze net lists. The net list can calculate activities from any of the net lists at the gate level you want to use for technology mapping, net lists at the LUT level, clustering, and BOE level for placement and routing. There are two types of values that this tool calculates: static property, SP, rate of signal high, and switching activity. Summary. In this chapter, we briefly summarize how the FPGA design tools are made and how the researchers carry out in the background. All of them are aimed at optimizing delay, implemented area, and power consumption. Even if the optimization is performed independently in all processes, it is not necessarily the optimum in the final circuit. That is, cooperation between processes if necessary. For example, it is possible to improve performance by simultaneously optimizing the technology, mapping, clustering, and by also processing the clustering and placing routing in the multiple processes simultaneously. Future FPGA design tools are expected to progress with the aim of simultaneous optimization of such multiple processes. Hardware algorithms. So, I'm getting close. How am I doing on time? Time check. Average Linux user needs to type date into console to get the time. 9 p.m. 2 hours. It's about a page a minute. Scheiße. Well, I'm not doing my nightly reading because I'm counting this as my nightly reading, so. Dang it, and I gotta do the compilers thing. Real quick. Let me just go ahead and do that. Dang. Dude, my pelvis is clapped. Tiger AR.
It's actually not super easy. All right, I'm gonna go to the bathroom and then I'll read this. So I just finished the compiler's worksheet. One sec. All right, let's resume.
That looks pretty good. Let me check people's office hours real quick. Мы когда Just take a little break. Слушать музыку. И так далее.
В моем доме холодно и темно, в моей голове пустота и мрак. Я не ощущаю совсем ничего и жду хоть какой-то знак. Все мои песни совсем не о том, все мои мысли как черный дым. За стеной у соседей все хорошо, и им все равно, что в глазах у них пыль. Я честен и искренен буду всегда, и это, наверное, моя беда. Я хотел быть другим, но уже никогда во мне не загорится та звезда. Я становлюсь старше быстрее и быстрее, все меньше ощущаю себя среди людей. Я так волнуюсь за завтрашний день, но я верю, что завтра я стану сильнее. Не общайтесь со мной, я так ненавижу это. Забирайте мою жизнь, оставьте кусочек лета. Ничего не поменяю, я уже не подросток. Мама, объясни, ну для чего я стал взрослым. Не общайтесь со мной, я так ненавижу это. Забирайте мою жизнь, оставьте кусочек лета. Ничего не поменяю, я уже не подросток. Мама, объясни, ну для чего я стал взрослым. Несовместимые вещи во мне создают проблемы и мысли о том, почему я стал именно таким, почему во мне этот дурдом. Серые краски, городской шум вводят в депрессию вечно меня, и никто уже отсюда не спасет, ведь в это вогнал сам себя я. Мне так надоело себя искать, наверное, лучше остаться никем и каждый вечер засыпать с мыслью, что я потерял еще день. Каким же буду через несколько лет, наверное, так же не изменюсь. Я обязательно об этом напишу еще одну песню про мою грусть. Не общайтесь со мной, я так ненавижу это. Забирайте мою жизнь, оставьте кусочек лета. Ничего не поменяю, я уже не подросток. Мама, объясни, ну для чего я стал взрослым. Не общайтесь со мной, я так ненавижу это. Забирайте мою жизнь, оставьте кусочек лета. Ничего не поменяю, я уже не подросток. Мама, объясни, ну для чего я стал взрослым.
pipelining exists.
Certainly.
It's like the upper bound F. The number of stages n is not much greater than that of processing iterations big N, and the speed up by pipelining remains much smaller than n. True, because you're still eating the delay of filling up the pipeline before you even get through it. E subpipe, E pipe, and big N, S pipe event. So yeah, I'm not too worried about. I'm not gonna be calculating that. Speeding is just fine, 50% max. Consequently, at the beginning of pipelining, yeah, you gotta fill it up the pipeline, and at the end, you gotta empty out the pipeline. The problem is if you actually care about latency. Clock skew. And yeah, that's very unrealistic. Your clock skew and your latency is gonna be collapsed, bro. Flynn's taxonomy. General purpose computer architectures in terms of concurrency degree and an instruction stream for controlling a data stream to be processed. And okay, so this is like computers, yeah. It includes single instruction, single stream, data stream. It includes single instruction, single instruction stream, single data stream, single instruction stream, multiple data stream, multiple instruction stream, single data stream, and multiple instruction stream multiple data stream. Damn. So instruction memory into the CU control unit, thank you, and the PU processing unit. So single, quite pleasant and understandable. Here you have multiple processing units and one control unit. Both axes are multiple, and you have one multiple instructions, single data. Because, yeah, you got to do them. That's a monad. Yeah, I'm shooting myself. But, yeah, okay. Although this taxonomy is oriented to general purpose architectures, it's useful for more general architectures of parallel processing hardware for recognizing instruction stream as control in a broader sense. That is true. I respect that. In Fluent's taxonomy, computer architecture comprises the four components of the processing unit, control unit, data memory, instruction memory. The SICD, SISD. Once you, yeah, we just read that. Consequently, single instruction does not perform parallel processing. Yeah, okay. SIMD. This is like the one you hear of. Oh, is that SIMD? Single control unit reads out an instruction stream and controls multiple PUs simultaneously. Each PU executes common processing based on common controls, but for different instruction streams. Consequently, SMD. SIMD is an architecture making use of data parallelism. The data memory can be accessed by all the PUs as local memories of the PUs, or as a single shared memory common to all the memory. Because the SIMD architecture is suitable to process numerous data synchronously with a single sequence of instructions, it is used the designated processor for image processing. Because you're just spamming the same thing on different data. Yeah, that's kind of makes sense. Okay. In addition, a microprocessor can incorporate SIMD constructions to provide itself with a function of parallel data processing. For example, Intel Corp, aiming at speeding up 3D graphics, designed a microprocessor, the Pentium MMX, with SIMD type extended instructions. 4 16-bit integer operations simultaneously based on one SIMD instruction. AMD now has a new product, 3D Now. Bro, just get a graphics card. Are you old or broke? Later, Intel processors were augmented with streaming SIMD extensions, SSE, for floating point operation. Then you got, so there's SIMD instructions that exist. MIST, which is multiple instructions, single data, which provides some sort of piping, yeah. Multiple CUs read out instruction streams that differ from each other, which control multiple PUs. Multiple PUs? Yes, they still have discrete PUs, or individual perhaps PUs, but they are going into each other. A single data stream successfully regarding it as a whole. It is difficult to find a commercial product of this type. Coarse grain pipeline. As we recognize, CUs provide different functions to PUs in performing parallel processing with MIST. It earns the designation of architecture for functional parallelism. Functional in what sense? We'll just say working, I believe that's what they're saying. Application-specific hardware such as an image processor array that executes different processes of conversion of pixel values, egg detection, cluster classification, and others forms each stage of pipeline corresponds to MIST type architecture at each processing operation. Yeah, I agree with that. I'm also getting bad at reading. Whenever I try to read at the process, whenever I try to say the words of the process that I read them, it just sounds like I don't even know what I'm talking about. So this is actually good practice. I've probably been reading on YouTube streams to 0 people for 100 hours at this point. Running MEMD in 6.3D, multiple CUs read out instruction streams that differ from each other, which control multiple PUs independently. Different from MISID, just multiple single instruction data. What is that? Is it MISD? I think it's talking about MISD. What is it? Multiple single instruction data. Am I tripping? Each PU performs parallel processing based on different controls and for different data streams. MIMD has an architecture simultaneously accommodating data parallelism and functional parallelism. So yeah, I believe it is talking about more carrying out the functionality of the program, you could call it. Might perform different processes for multiple data based on different instruction streams. A tightly coupled multiprocessor like a symmetric processor symmetric multiprocessor (SMP), shout out SMPs, for which multiple processor cores are connected in a common memory system is an example of MIMD type architectures. A cluster type computer in which computation nodes made of memory and microprocessor are connected by the interconnection network is another time. Systolic algorithm and systolic arrays. Systolic algorithm is a general name for algorithms in which a systolic array is in which systolic arrays are used to realize parallel processing. A systolic array is a regular array of many processing elements for simple operations. It has the following characteristics. PEs are arranged in arrayed in a regular fashion. They have the same structure for a few different structures. PEs are arrayed in a regular fashion. They have the same structure or a few different structures. So I'm kind of just reading. That is a common theme in this book. I'll read a word, read a lot of information about it before you know what the word means, because actually understanding the word is kind of derived in some image that is on a next page or paragraph. 1D systolic array, tree stuff. So yeah, I'm just gonna have to look this up. Systolic array. Network of processing units to perform computations. Nah, this looks like it's out of I guess that just looks like a paper or a book that I read. This same junk. Dude, it's a local file, bro. I don't think this has systolic arrays in it. If I did, that's embarrassing. Doesn't appear so. Oh, it does. 666. No, dude. Plus 26. Oh, I messed it up. Systolic array. It was used in the context of a combinational binary multiplier. Systolic array. Systolic array in 1014 is attractive because it has a regular structure of identical cells and easily accommodates expansion to... So it's like a bunch of individual units that are composed to make a bigger thing. Bet. See, I read that. I read that. So there are quite a lot of them. So PEs are arranged in regular fashion. They have the same structure, a few different structures. The neighboring PEs are connected, allowing the data movement to be localized with the connection. If a bus connection is used in addition to the local connection, the array is designed as a semi-systolic array. So yeah, it's like a chain of them, and they preferably do not communicate far from each other. They just communicate with adjacent ones to accumulate some operation between them collectively. Single clock signal. Operations in the processing element and the data stream caused by the data exchange between neighboring PEs resemble a bloodstream driven by the rhythmic systolic movement of the heart, hence the name systolic array. It's also designated as a cell. Okay, that's true. The systolic array can scale the performance according to the array size by arranging PEs with simple structures, and likewise data movement is suitable for the implementation in an integrated circuit. Many applications were proposed for systolic arrays in the 80s and 90s. You have some algorithms. 3 types. 1D arrays having a linear array. That's just like a pipeline. Though, not really, because you're kind of assuming that they're on the same clock signal. They're on the same clock edge, right? Or is that even true? Ugh.
Read. Okay, I'm kind of cooking with it. I'm kind of getting good at this. Muggy. I kind of have solid intuition right now. 1D arrays having a linear array. 1D arrays having a linear array. Okay. 2D arrays having a lattice-like array or a tree structure array with a tree-like connection. Many systolic algorithms for these arrays have been suggested, including signal processing, matrix operations, sorting, image processing, stencil calculation, that's a new one, and calculation in fluid dynamics. Although the initial systolic array assumed hardware implementation of fixed structures and functions, a general-purpose systolic array with a programmable or reconfigurable structure was proposed later. Curious. Classification of systolic arrays in terms of general versatility as shown in table 6.1. So 2D, 1D, tree, and yet some algorithms. Language recognition. Language recognition. As in spoken language. That's quite curious. I want to read that. I want to read that paper. Systolic array language recognition. Really? Wow. 1986. SMO. SMO. Wow, systolic array architectures for connected speech. So this is like digital signal processing. Yeah. Wow. That's kind of crazy. Two-dimensional systolic arrays. So, it seems like there's a lot of state in that. This is among the biggest skim you've ever seen here, but read accumulator instructions. Oh, shout out these dudes. Probabilistic matching algorithm. Both methods, advantages of these. Is it like there's a systolic array for each language? And you accumulate. That just sounds really crazy. I'm probably straight up capping. Problem is I don't want to read the whole thing. I just want to skim and learn everything that it says. Which just is an oxymoron. Damn. Dude, if I had infinite time, I could get quite good. Go to just read every paper, bro. But yeah, it's impossible. So, back to this. In this table, programmable denotes the capability to dynamically change the function of the circuit by programming the fixed circuit. We're talking about a different table here? Yes, okay. Can't wait to destroy my neck reading this. Oh, that's why we hit it with a... Oh, with leech. The classification of systolic arrays. Very few instruction stream. Multiple data streams. Yeah. Not really sure what that is. Reconfigurable is the capability to statically change, say, frick the table. Kong proposed the wavefront array, introducing the data flow to a systolic array to cope with this. Oh, so let's actually read that. With the increasing scale of the systolic array, high frequency operations with globally maintained synchronous. Yeah, that's the problem. Became difficult due to the propagation delay of the clock signal and other factors. Kong proposed the wavefront array, introducing data flow to a systolic array to cope with this difficulty. In his method, a PE designed as an asynchronous circuit operates with its own without the synchronization to a single clock signal. Furthermore, the data exchange between neighboring PEs is done using the handshake method. Examples of systolic arrays and algorithms for 1D and 2D systolic arrays are introduced in the following sections. Partial sorting by 1D systolic array. An operation of rearranging a given data row according to a given order is referred to as sorting. Okay, sorting operations are important and used in many applications. Here we introduce a systolic algorithm that rearranges. That's curious.
How would you like a I'm not gonna jump to conclusions. That arranges the given data row for n numerical elements in descending order and returns the upper n data. That actually seems like a lot of concurrent access of memory, so I'm curious. Figure A depicts a 1D systolic array and its PEs, which partially rearrange the upper n data. Unsorted values. Move to the right. Sorted values move to the left. Oh, so it's like a bubble sort. It's like a hardware bubble sort. Yeah, it's like a hardware bubble sort. Right? You swap. Wait, that's kind of dope, actually. Hardware systolic bubble sort. That's kind of dope. I mess with that. No, I mess with that. That's kind of cool. X in, X out, Z out, Z in. And it doesn't really matter that you're repeating the computations because it's just in parallel. Wow, that's kind of clean. That's kind of dope. That's actually quite intelligent. That's pretty dope. That's pretty cool. I'm not finishing this book tonight, am I? $10:15, an hour left. I'm not going to bed on time tonight. I'm finishing this before we go to bed. Yeah, I understand the intuition. Partial sorting of data takes n plus n minus 1 steps. But this could be so fast. Your clock can still be so fast that it's not as parallel as you kind of want it to be. And you also have to know the size. It's interesting, but I'm not sure how it compares. So you reset to the possible maximum negative. So now we're matrix multiplying. So I think I skipped something. Oh, we're talking about sorting, bro. Okay, so now we're doing a vector product of matrices by 1D systolic array. Ooh. I need to understand this. A 1D systolic array can perform the operation of vector product y equals ax. The operation of an n by n matrix requires n PEs. The systolic algorithm used for vector product of n equals 4 matrices is depicted in figure 6.6. So PEs, what is the PE? These lines don't make sense to me by default. We're expecting the output of y's given the x's. So we do one, oh, we're pipelining through them. So we're doing one. So 1 goes through, 2 goes through, 3 goes through, 4 goes through. And then while we're doing that, the A's come down. And it takes 2n minus 1 cycles. Or 2n minus 1, yeah. In PE's arrayed in the 1D row, the operation proceeds as follows. Elements in X enter the left end PE, whereas elements in matrix A enter each PE from above, both successively. Yeah. Each PE has register yi to keep a temporary value of the element in the y vector. Ooh. To keep a temporary value of the element in the y vector in addition to input x element of vector x. Each PE has a register y sub I to keep a temporary value of the element in the y vector. So you're like accumulating it over each sample of x multi. Ooh. No, that's clean. That's really clean. That's really clean. No, that's really clean. That's kind of cute, Loki. All P's execute the calculation of yi equals yi plus ax. So you're just accumulating ax. Damn. At the beginning of each upper, so it's a or it's a add and accumulate. It's more of add and accumulate. Or not more of it. That is quite literally what it is. At the beginning of the operation, yi of each register is initialized to 0. Then y equals 0, a sub 11. A sub 11? What is... Oh, it's column row. Row column. It's row column. Yeah, that makes sense. It's calculated in PE1, both in parallel. So 2n minus 1, like I was saying. That's so dope. No, that's so clean. Product of matrices. Okay. Okay, that's... So you need to n by n, PE, you need 2D. Ooh. Nah. These guys are kind of good. So this is a Mac. Yeah, I can't really envision the PE off the dome. But you have, so you start at the top where in, and then you send these down. That's a little harder to visualize, but every cycle this goes in both directions, yeah. Or the B's go down. So B11, B11, B11. And then these are offset by 1, so you go here, here, then you get here, 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 and then it's on parallel. Damn. That's kind of dope. 2D with a lattice, it is possible to perform. Dude, stop freaking spamming me, bro. Been a long way to go. 80 pages, effectively 70. But I haven't, it's been a while since the last 30 pages. Ой, я хотел сделать... So the 2D systolic array, and since you're like crossing your pipelining of the values, what do you call it? Indices of a matrix? What do you call values? What do you call the values in a matrix? Call them entries. Okay, entries. So as you pipeline the entries, you're pipelining the entries of A and the entries of B to produce C in two directions, and so you need the 2D lattice and hence n squared PEs. So here you see it with 4 as a vector product of matrices done by, as in the vector product of matrices done by the 1D systolic array, row and column elements are input from left and above top. From left and above top. Dude, some of the grammar and largely just grammar in this is quite curious. Like, do they even read this before publishing? Shifting rows and columns, but I do appreciate the knowledge of it. The function of a PE is the same. Really? Because what do you do when you multiply a matrix? That's probably next lecture on the notch too. What do you do? You get the column of this, and you transpose that, right? Transpose into like a row of the second one, and add it. And you do the same. So you add, yeah, it is just accumulating and add. It's the same PE. Wow. Yeah, so this is kind of dope. Systolic array for stencil computation and fluid simulation. Although the examples introduced in the previous sections were those of simple PE operations, programmable systolic arrays oriented to many stencil computation. Yeah, I don't know what that is. And for computational fluid dynamics and others have been proposed. The structure of systolic computational memory array of a systolic computational memory and its PE design for stencil computation is shown Fig 6.8. This array has a 2D scheme of vertically and horizontally connected PEs. So let's look at the processing. Let's look at the higher level first. So that's that's certainly something. Can't really tell you what it is. We have a array of PEs. So this looks quite generic. We have a sequencer. We're sequencing. We have 9 sequencers inputting into a 2D matrix of PEs that we're categorizing into 9 CGs, a control group, and each PE has some local memory, a comparator unit, I believe, comp unit, and a switch. a switch with 4 inputs and 4 outputs. So input and output to each adjacent, or at least for the inner ones. Either way, it's still input and output to each of the adjacent PEs. And takes as input a sequencer. So, okay. What is that? So yeah, to send data in all directions and a sequencer to control those elements using a microprogram. Because each PE has a large local memory and because the whole array is a memory not only for operations but also for data storage, it's considered as a computational memory. The computation unit can execute floating point multiplications and additions. See, I couldn't tell you how to map any problem to the structure, but I understand both independently. Like I could tell you what I'm just, but by understanding, I mean I can just read what it says. Like, the computational sublattice data. Yeah, I don't really understand the problem space either. Like, what is stencil computation? But I'm not too worried if I don't know that. So we'll just skim. You know what I'm saying? P microprogram working data operations. So boundary condition, same stencil. Okay. Pseudocodes for the 2D stencil computation. Okay, so that's kind of useful. It has a triple loop structure consisting of loops for vertical and horizontal directions and one for iterating them in a time step. So for n, j to y, where's j defined? Sorry, I'm so slow. I'm cooked. So I meant where's y defined? I meant where's y defined? Trust. Y is the length of the y-axis, and x is the length of the x-axis. Okay. So for grid traverse, I could have just read the guide and shut up. Update grid value from n to n plus 1. What does this do? F of n plus 1. J. It updates the grid value from n to n plus 1. What is v? It represents any operation using data stored in a stencil. So it's like a region of xy. Weighted coefficient. I'm okay not understanding the problem, but it looks like we're applying some scalar multiple to some region of a grid. Okay. The repeated stencil calculations of different coefficients shown and competition. Okay, whatever. The data flow machine is a computer architecture that directly contrasts. Oh, no. That directly contrasts the traditional von Neumann architecture or control flow architecture. It does not have a program counter, at least conceptually, and the executability and execution of instructions is solely determined based on the availability of input arguments to the instruction, so that the order of instruction execution is unpredictable. Interesting. Figure 610 compares the data flow machine with a von Neumann one. Since the data flow machine has no instructions, it can eliminate the bottleneck caused by the instruction memory faster than modern computer architecture instruction time. That's kind of dope. Although no commercially successful general purpose computer hardware has used the data flow architecture, it has been successfully implemented in specialized hardware such as in digital signal processing. Okay. Because the instructions are implied by the data's passing into the circuit. Network routing, yeah, likely. Graphic processing, telemetry, yeah, that's true. This is quite common. The data flow machine executes not for so it's not common for general purpose computer hardware because you're abstracting. The whole point of general purpose hardware is that you're abstracting access to low level details via the instruction set, which is you can implement any program. You know what I'm saying? The data flow machine executes the data flow graph for a given program as shown as figure 611. Fork copies the given data. So we're not spawning a new process, sadly. Primitive operation outputs the result of the executor operation. Branch executes a conditional jump corresponding to the signal true false, and merge selects the signal corresponding to the conditional signal. So it is kind of like because you're merging back from a fork, yeah. What does fork do again? Copies the given data. So I guess implying it is kind of like fork in a traditional sense, and now you're copying the data, not just for no reason, likely be used in parallel in some other operation, and perhaps the primitive operation, yeah. Fork. Primitive operation is just a generic function. Branch and the inverse is merge. Chill. Figure 612, which is below, so we'll get to that. Shows the data flow graph which executes the operation shown in figure 610 and figure 612. Circle denotes the data to be executed and it's called by the token. Here we show the value of the token in the circle. First, the adder starts the operation. Since two tokens have their values, then it generates the execution result. Next, the ladder multiplier and subtractor starts the operation since it has received the input token. In this manner, it is possible to easily know the inherent data parallelism in the program to be processed. Similar to the von Neumann machine, the data flow machine can realize the conditional jump and loop operations. Figure 613 shows an example of the conditional jump. It can be realized by the branch and merge nodes. When the token arrives at the branch node, it executes the branch operation, then it sends the token to the selected operational node. Finally, the merge node selects the output corresponding to the merge node selects the output corresponding conditional signal to the conditional signal. The output, so we can imply the meaning of that from the graph, I believe. Figure, sorry. Finally, the merge node selects the output corresponding conditional signal. So the version. So x and y, we have two inputs. We're adding them. We have a statically defined, a partially applied, perhaps. We have a partially applied subtraction function, and we are squaring something. And we get 5. We get -1 and 25. So that's the fork here, yeah. So we're forking to two operations. Your branch operation for data flow graph. And we also have a, sorry, that was a data flow node. No, at the bottom, 613, we're looking at a branch operation for a data flow graph. We're evaluating 2 bits x and y. Cond between them, I'm unsure of. Or it looks like I'm not sure why cond is in between them. That's curious. But x and y, if t is, if x true, op 1. If y false, op 2. If either is true, put them into either op. Either true, op 1, either false, op 2. Then use the cond to multiply. Okay, so I should probably just read this. If cond equals t. Oh, so x is going, so cond is kind of passing x through. Yeah, okay, that's kind of curious. So yeah, I didn't see cond as something, as a third input. If cond is true, do op 1. If false, do op 2. And then and then cond multiplexes on T and F. Yeah, because once you still have them in parallel, so you need to still multiplex on them. So it kind of has you have 3 multiplexers despite only doing 2 functions and 2 variables. Okay. Updating the initial value at the merge node, it repeats the execution node through the branch when the condition is satisfied. There are 2 types of data flow machines that realize programs including loops. One is the static data-driven method, and the other is a dynamic data-driven one. Shout out. No, this is so real. Inner hyphen indecisiveness. It's a goated condition. Static one expands all the loops and represents them as a flattened data flow, while the dynamic one shares the execution unit with the processing of the subsequent units using the data flow of the loop body. In many cases, since the size of the data flow graph becomes too large to realize it with a data flow machine which has a limited hardware resources. On the other hand, the dynamic execution nodes in the loop body are shared by computing units. Control unit must be provided. Yeah, I was about to say, I don't really see how you do that without some instruction-ish construct. Otherwise, if multiple tokens between iterations exist, it is not possible to guarantee them. So here we have a loop operation for a data flow graph. So we have a condition. If this condition is false, we return X. Otherwise, we loop back up. So it's a lot easier when you read it. Tagged tokens. Colorized as well. Operations on tokens with the same tag being guaranteed. In the static data-driven method, is often used to represent the operation and the operand of a node in a mixed manner in the data-driven operation provided by Dennis. Dude, shout out Dennis, bro. The node information of the data flow graph has the necessary data for the operation, the storage type of the calculation, and the destination for storage. By using this node information as a token packet, so I'm not really sure what they mean by token. It is like a key stored with the integer value. Token to DNet. Yeah, I'm not really sure what's going on there. The destination for storage. By using this node information as a token packet, the data-driven processing is realized. Note that the token does not have tag information. It focuses on the static data flow, which does not include the loop processing. Figure 615 shows a hardware structure and each operand cell for the static data-driven infrastructure. In Fig 615A, the operand cell stores the above information and it represents the data flow graph as an instruction of the data-driven machine in the whole instruction having valid information. Hereafter, we explain the processing steps. Let's do it. When the operands are complete, the operation packet is sent through the arbitration network. This packet includes all information of the instruction cell, the operation type, and the storage destination for the result. The operation's result is transformed as a data token through the distribution network DNet. Then it is written to the operand part in the instruction according to the storage destination D1, D2, and Fig 615B. Next, the instruction with the operand sends the operation packet at any given time. By following these steps, a series of data-driven processes is done. The architecture of ALU dot. Yeah, some of this dot 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 I'm unsure of, or perhaps it's multiple of them. You have many ALUs to a CNET, to a DNet, and an ANET. So I recall these words, but what is it? Arbitration network goes back into the LAU and back into the DNet. Yeah, I'm gonna say I don't know what that is and not care. And for the dynamic one, let's do some skimming. Separating the execution unit and the operation. Loop processing can be considered raising a tag token. So I didn't understand that. If I need to, I will come back. Shout out things existing only untransiently. Not remove the word only. Dude, I want to finish this so I can start doing the homework. These dudes are getting absolutely mogged on Piazza right now. What is it? I think it's fine. Basically, it's only match. No, tomorrow morning. I'm switching this to tomorrow morning. Tiba. All right. Distractions. So I'll probably finish this. I want to take a shower before I go to bed. Okay. Petri net, also known as a place transition PT net. Let me get a bath. Casual bath. My tea bag's cooked. It's been like 5 hours. Okay. I thought PetriNet was some like derivation from place transition net. Trying to compute that. Got a athletic Mexican style. This was Whole Foods. Yeah. Okay. Directed bipartite graph. What does this mean again? Yeah, I had that image in my head. I was just like, events may occur and they're represented by bars while conditions are represented by circles. Chemical processes, curious. So I don't care about that. Small chapter. Stream processing. This I need to pay attention to. Stream processing data element. Should have put this in the above section, bruh. As I've learned in another book, this is a overloading of the word kernel, as in the piece. So we had some Pertinet algorithms. I don't really care. Input stream, processing kernel, outputting stream. And you can nest them as Punt Engine does even. Look at so consider Punt Engine. Taking a stream of market data, accumulating an order book, even producing output that's orders after accumulating some other metrics, some accumulation of the, excuse me, price perhaps, you know, buy. Let's make a order if there's, make an order if there's a certain price. These instructions can rapidly process vector data of definite length. Oh, you're speaking, so I think I skipped something. Incorporate vector. So what's this sentence? As a means to accomplish stream processing of high throughput by implementing software, it's possible to incorporate vector or SIMD instructions into general purpose microcontrollers. Yeah. Hardware, yes. In parallel, yes. Pipelining, systolic algorithm, and data-driven approaches. Lost my page. Blunder announced. Dude, Hideharu Amano needs to get fired, homie. Or he's the editor. Because this is a collection of things by somebody else.
Playing freaking Valorant, dude.
Is that regular expression matching? Dang, I still got so much to read. I'm not getting sleep tomorrow, dude. It's not a country. Where's that? Where's that? So, designing a high-throughput stream processing hardware user depends on a lot of operations in parallel. This implies the use of pipelining, systolic algorithms, and data-driven approaches. Kernels designed as pipeline modules can be connected to each other and thereby statically implement a giant pipeline. High-speed stream computing can be achieved where sufficient hardware if not available. Different kernels share the same resources. Ooh. You switch modes to save resources. I don't know about that. Folding. Okay. Reason folding, the hardware works in time sharing mode. First, the processing of kernel 1 for the input data occurs. Then the mode is switched to execute kernel 2. Similar processing is done for kernels 3 and 4. So you gotta process 1 on an odd cycle, then an even cycle, then 3, and 4. Sorry, that's the folded implementation on the left. So you 1 and 2, you do 3 and 4, and then time domain multiplexing. So that's probably something that I haven't gotten to yet, yeah. Although the cycle time is doubled and the throughput decreases by half with a small amount of hardware resources, stream processing can be accomplished. I mean, sure, you decrease. I mean, that's kind of dumb. Oh, if I had hardware that could make this twice as fast, it wouldn't be half as fast right now. Like, bro. In the example given above, all kernels work all the time, and the operation rate is 100%. In this case, the operation rate of the folded processing kernel node is greater than 100%. Operation rate of the folded processing kernel node. Is it greater than 100%? Where's the operation rate? Define this. Okay. However, as in the case of conditional branching processing, the rate of operation is naturally less, even if aggregated. 623. See, I have no idea what we're talking about time domain splitting. The hardware works in time. So it does this. So it does odd, even, odd, even. Okay, so this is just breaking it further within these. Okay. I think we're chilling. There you go. Even so graded with the operations of other kernels. Under these circumstances, the hardware resource consumption might be reduced without lowering the rate of operation at the expense of a complicated control. Figure 623. So let's just peep that real quick. So we have stream processing with conditional branch. So we're processing kernel 1 as a function of x, y, and z. We do one thing 90% of the time, another 10% of the time. We mux on between them with some thing. And time domain multiplexing, or sorry, is 90% and 10% the. We'll have to see what that is. Processing kernel 1. Instead of performing the operation like that, multiplex on X and Z, and Z and X as selected. Ah, huh. Ooh. So yeah, this is like a bit of deduplication of the hardware, yeah? Or I think this is the same representation for the same thing, actually. No, it's not. Let's read. I've been exposed. Let's read. Figure 623 demonstrates a simple example of folding with a rate of operation which is less than 100. Figure 623A, including conditional branching, two operations are performed simultaneously. The signal selector outputs the results of the operation in two kernels, in two kernels with proportions of 90% and 10%, respectively. Accordingly, the real operation rates of both kernels are less than 100%. For this case, a module that can process both formulae while considering common operations can be implemented. The computation unit is shared in this design. Figure 623 illustrates an example. A multiplier and an adder are implemented for each formula, and one selector is inserted to switch the operations of the formula. Only one operation is necessary for one formula. Therefore, the consumption of hardware resources can be reduced without increasing the number of cycles for one processing iteration of one element of stream data. In addition, a stream processing iteration, where some dependence relations exist between successive elementary processing iterations, might be implemented by inserting a delay buffer memory. This buffer sends intermediate data stream. Oh, okay. Excuse me. So it's like collecting a buffer of them before processing. So let's stop at this. So since we're in either case we're multiplying by y and adding the output of that to either z or x, and then you're multiplying by the which one you didn't choose to add. So that's kind of smart. Kind of mess with it. Moving on to 64. Where was I? Stream processing iteration where there's some dependence between successive operations. Processing iterations, better. You can have a delay buffer. The buffer sends intermediate data of the stream processing to the next elementary processing iteration in a delayed fashion. In the example presented in 64, in addition to the current output result from a processing kernel 1, delay buffer memories to send past data. Delay buffer memories to send past data of to what? Delay what is a sentence, bro? In the example presented in Fig 624, in addition to the current output result from processing kernel 1, delay buffer memories to send past data of to processing kernel 2 are inserted. Delay buffer memories to send past data of 2. Delay buffer memories to send past data to kernel 2 are inserted. I think that's right. So this should probably say kernel 2, yeah? It should say kernel 2. Then we have delay buffer memories. So we want the third element. We want the current, for each element, we're making some operation with it itself. It appears. E of I minus 1, and E of I minus 3. Okay, so delay buffer, that kind of makes sense. So, stream processing hardware for averaging a series of scalars. I've written that. Shout out. Though, I'm not using division like that. Using a circular buffer. And shifting by the natural log of its size. Or the log base 2 of its size, better. Stream processing hardware for averaging a series of scalars. So we're considering this a processing kernel. We have accumulator, was accumulator plus n. So this wants it over an infinitely large amount of time, it appears. Accumulator slash num total. Can you do that? Is that what that is? I don't think that's what that does. you're forever increasing your accumulator, but that is what that does. Yeah, I thought this said ACC. That 3-star stencil. Okay. Skipping the 2D stencil junk. Skipping the fluid dynamics. I'm skipping the fluid dynamics. Cellular automaton. Repeatability theory, mathematics, physics, complexity science, theoretical biology, and microstructure modeling. So can't say it's useless, I suppose. Neck check. This Conway? As a Taurus. So I definitely want to save page 29. Von Neumann. Von Neumann himself? Damn. Oh my god, it's a book. Dude, Von Neumann was cracked. How do you write this and do computer job? I guess the thing is that it's the same. Or related at the very least. Yeah, I'm not reading that, but respect to Von Neumann, bro. See, it is annoying to implement a boundary because there's a lot of rules. Okay. Implement as a Taurus. I like how you're supposed to like click this link and read a 400-page book from like 1960. And a misclick. You hate to see it. You hate to see it. Oh, you hate to see it. Okay. So you up it, Bears? I'm glad to see sorting brought back. That was kind of interesting, the Bulbasaur. Let's go. I recognize that. No, it's not very impressive, but... So I know what sorting is. Numerical and lexicographical. Lexicographical. FPGA-based hardware accelerators for sorting using database image processing, data compression. Merge sort tree. Ooh. So the Bulbasaur was kind of easy, lucky. But it was kind of cool to see. Takes a ton of odd even merge sort. Merge sort tree. Binary tree where each vertex is realized by the EU, European Union, sorry, exchange unit. The circuit has many FIFOs in the input and output and performs the sorting in parallel. Marge sort.
Bro, shout out Marge Sword, bro.
Now I'm a big Marge head.
I'm a Marge main. So how does this work? 4 2 1 3 1 2 3. Okay, so these are the inputs. EU 2 4 1 2. So it swaps them. Take it in, swap. Here, swap. So they're chained, or they're like daisy chained with themselves and their inputs. And then they are. Okay. So you have a bunch of them, they're flipping themselves.
4 elements, the network. So here's the tree one. You have EU and EU. And then 2 and 1 here. And then 4, 2, 3, 1. So when you filled it up, then you got the next sample, and when the 4 came in, the 4 and the 1 came in, you start at the bottom, I guess. You put the 1 because it's the lowest, sure. And then you put the 2, and then you put a 3, and then the 4, okay. Killer applications of FPGA is pattern matching, which finds a given pattern in the data. Exact, regular expression, and approximate. Emulator. Neg check. Index generation function f is shown in Fig 632 and 634. Shows the decomposition chart for f. In Figure 634, the label in the right side denotes x1, 2, 3, 4, 5. So this is something. Left side is x2, 1, 6. Boostero. So I'm not really sure what we're talking about here. They were talking about matching stuff. We're talking about x equals 2 labels or something. Okay. Do this. You first store the. You just compare. Yeah, so I'm quite lost. Wait, this is actually part of the homework I was just talking about, but this is like way overkill. Example of an index generation function. 5, 1, 2, 3. No idea what that is. Main memory. Yeah, I just don't understand that. Whatever. That's fine. Character and a meta character. Set of strings. Various network applications use malicious data and packets regular special massing. Considerable fraction. Dude, shout out Perl. Hundreds of megabits per second, which is too slow for most applications.
detected by finite automata. Finite automaton for each state by their unique transition. While in a non-deterministic finite automaton for each state in each input, what transitions may exist, and in NFA, there exist epsilon transitions. Is that epsilon? I don't even know. This kind of got very specific. I don't really know what to make of this. Some very particular algorithms. And we have string ABC, so this is quite abstract. Yeah, I'm skipping that.
Approximate matching, an edited pattern in a text. Based on dynamic programming. Evaluate similarity between the DNA sequences. Compute the edit distance.
So this is more simple. There's only 3 possible things. There's not a lot of state. OSPC, read the text in the buffer memory. Address into the text index to get text. That's the disk calculation. Get that in the controller. Put that into a FIFO. Push that out. Controller. Also, perhaps indexed by the host PC. And the algorithm is a matching graph of the text to the pattern. I mean, this could just be a table or anything. You can just spam V. Get a vertex in this graph. From C to. Okay. Programming, yeah, that's true. Let P equals P1 to Pn be a pattern, T1 to Tn be text. Is a matching graph in a approximate string which has n plus 1 times m plus 1 vertices. For coordinate ij, a vertex is placed. Assume that the upper left is 0, 0, and the coordinates ij increase towards nm. For a valid index within the bounds, their edge is connecting it to the other ones. And so, YSDL, the editing score for deletion, sins the score for an insertion. 1, 1, 2, vertex subpattern. Define that the vertex coordinates editing each score for the vertex. So I'm not too concerned by this. Yeah, I don't really care about that. And it's much less than yeah, that makes sense. Processing element. So the naive method. I'm just gonna call that okay. So I'm in the final 50 pages and I'm tired. All right, practical application. So this, we're gonna speedrun it. I'm not giving up. I didn't come all this way. I didn't come 8 hours to give up. If you thought I was gonna give up, I almost did. But not today. So we're gonna skim this. At least 7 advanced devices and architectures sounds useful, but the practical application of programmable logic devices I think can be largely implied. So let's see. They're mostly used for prototyping. Now you can do other stuff like high frequency trading. Indeed. See, I'm just gonna read. It kind of slows me down when I talk. Shout out HPC. I don't really do anything with HPC, but that was respect. Those got some cool going on. Network switch. Search engine. HFT. Shout out HFT. Space debris. Okay. HPC. Got that effectively in my PC right now. Talking about teraflops and all that. Yeah, I don't care at all. They got a lot of them. The network. Performance upgrade is a network chip. So I think I've had a few FPGA-based network chips. And I think they were actually microcontrollers. Just like some cheap, crappy one. Software-defined networking. So the situation is that SoC makes you change it. TCP, UDP, yeah, that's trading club right there. Yeah, part of the address in the subnet. Big data web search. Bing is crazy. Wow. Work on a hit vector. It's multiple instructions, single data. Ooh, 600 microsecond software, 4 microseconds FPGA. You got the genetics matching thing. So high frequency trading. So I know what stocks are. Going to the bathroom and brushing my teeth before the final chapter. I'm tired, dude. Advanced devices and brand new architectures. Asynchronous FPGA, which can be the breakthrough of high performance operation with the power consumption handshake. 3D, 2.5D. Drastic IO increase. CGRA's coarse grain reconfigurable architectures. That's crazy. Virtual hardware? That's kind of dope. Using video cameras. That editor looks atrocious. C to RTL. Use Haskell. Use Haskell.
Doesn't use a dynamic network that always transfers the clock posts, nor does more within it. The average as well. That's kind of smart. Bundled data, 4-phase dual rail, level encoded dual rail. $870 a delay buffer. Four-phase dual rail. 1 bit for data and 1 bit for request signal. Receiver sends the 1 bit acknowledged signal back. And you have spacers. Dang. Clock data recovery. Optical.
What is holographic memory? Yeah, I don't know. Alright, that's it. I skipped over the optical stuff because I don't care. Frankly. But, yeah. So. 8-hour stream. Damn. Look at this kid, man. Tell me I won't be a great programmer, bro. There ain't nobody working as hard as me, bro. Alright, let me go to sleep. See ya.